Hello students, I am going to teach you hydraulic machines. Hydraulic machines is in fact a separate subject for ESE, but for GATE point of view, weightage for this subject is less. So we are not studying this as a separate subject but as a chapter. If you see the previous GATE questions for civil as well as mechanical engineering, almost every 2 to 3 years you will get one question, and that too mostly around 50 to 60% of the times the question will be theory question. So if you know little bit about hydraulic machines, like I'm sure you have already studied hydraulic machines in your BTech. Once you have gone through that subject in BTech, based upon that knowledge, so most of the theory questions you should be able to solve. Rarely there is a numerical. So I recommend for GATE aspirants not to invest your too much of time for hydraulic machines. So instead of that, you can study other topics, because hydraulic machines is very vast, and to master that hydraulic machine subject, it requires a lot of time, and in GATE its weightage is less. That's why it is not wise to spend too much time on hydraulic machines. So whatever we are going to cover in this chapter, that will be more than enough for GATE point of view. So what I recommend is just once go through our video lectures, that will be more than sufficient for GATE point of view. Now briefly I am going to list here syllabus for hydraulic machines GATE. So basically we are going to study 3 turbines: Pelton turbine, Francis turbine, Kaplan turbine, the important topic in this chapter is similarity laws. Similarity laws, and the last topic is cavitation. Okay. So in GATE syllabus there is no pump, there are only turbines and another extra topic related to this similarity laws. Okay. I'll give relative importance of each topics by highlighting these topics by stars. 5 star means most important topic. So overall weightage of this hydraulic machines is less in GATE. So chapter itself is having weightage, you can say 2 star. Out of 5 star, weightage of this chapter is 2 star. Now in this chapter, if you see the previous questions, maximum questions will be coming from similarity laws. Okay. So here I am giving weightage for this similarity law 4 star out of 5, 4 stars, because maximum numerical questions chapter it is going to come from similarity laws. Remember, weightage for entire chapter is 2 star, and in this chapter weightage for this similarity laws is 4 star. Okay. Then Pelton turbine, then Francis turbine, then Kaplan turbine, and cavitation I can say 1 star. On cavitation mostly you will get theory question only. Okay. If you see the previous GATE question, if you in last around 20 years, Pelton turbine has got only 2 numericals till now, 2 numerical questions. There are some theory questions, but numerical questions on Pelton turbine only 2, civil and mechanical including, I am telling you. On Francis turbine only 1 numerical, and till now since 2007 there is no numerical questions on Kaplan turbine. Okay. On similarity law there are 5-6 numericals. So why I am highlighting this? Because many people think hydraulic machines as very difficult subjects. In fact it is difficult, but GATE point of view you should not invest too much of your time studying this subject. Okay. Now briefly I will introduce myself. My name is Achyut Bhore. I was all India rank first in GATE 2008 in mechanical engineering stream. I have total 10 years of experience, out of which 2 years of industry experience and 8 years of teaching experience. I am working with ACE since last 4 years. For you, for GATE English, I am going to teach hydraulic machines chapter, and for Hindi version maybe entire fluid mechanics course teach, and hydraulic machines for ESE there is a separate subject, right? Hydraulic machine for ESC is a separate subject. So that entire subject I am going to teach for English as well as Hindi. This is Pelton wheel. So jet is coming out of nozzle with high velocity. High velocity jet will be striking on bucket. When jet strikes on bucket, it gets deflected due to bucket profile. And due to deflection, there is change in direction. Due to change in direction, there is change in momentum. And as per Newton's law, whenever there is a change in momentum, there has to be force. This is working principle of Pelton turbine. In fact, for all turbines, be it Francis, Kaplan, or even gas turbine and steam turbine, working principle for all turbines is same. To generate force or torque, you must change momentum of a fluid. Otherwise, there is no force or torque is possible. And rate of change of linear momentum is equal to force, and rate of change of angular momentum is equal to torque. So this is working principle for all turbine. So this is real image of Pelton turbine when it is working. You can clearly see the jet is coming from nozzle, and then it is striking on the bucket. You can see there is some cut at the bottom of bucket. That cut is to allow jet to bypass so that it can strike on next bucket. You can see the splitter also. When jet is striking on the bucket, the splitter is at center, there is some ridge that is called splitter. On splitter, jet will strike. After striking, it will get deflected into two equal parts. And when jet is passing along this bucket, there is continuous change of direction. So due to this change in direction, there is impact force, and that force is responsible for driving Pelton wheel. This is real image of a working of a Pelton turbine. So camera is placed below the Pelton turbine and it has captured the picture. So you can see the jet coming out of the nozzle and it is striking on the bucket of turbine. So you can see some ridge at the center bucket, that is called splitter. The straight ridge, that is called splitter. On splitter, when jet strikes, it gets divided into two equal half parts, and then jet travels along the bucket. When it is traveling along the bucket, there is continuous change in direction, and due to continuous change in direction, there is change in momentum. You can also see there is some undercut at bottom of bucket. That undercut is to allow jet so that it can strike on the next bucket. So in this way, interference of buckets to the jet flow will be minimized. Same thing can be represented pictorially in terms of diagram. So jet is coming from nozzle. At center you see the splitter. So this is cut section view. So you can see the splitter at center. Then jet gets divided into two equal half parts. Then jet travels along the bucket profile. So due to change in direction, there is change in momentum. Okay. So at the exit, velocity triangle is shown. So we'll discuss in detail more about velocity triangle later. For the time being, you can just remember that there are two velocities of jet. One is with respect to bucket, another is with respect to ground. With respect to ground is called absolute velocity, and with respect to bucket is called relative velocity. So whatever this blue line is shown at the exit, that blue line, that jet part, it shows absolute velocity. It means when you observe the jet with respect to ground, you will see this kind of jet. More details of this velocity triangle we'll discuss later. So same diagram is drawn here. This is penstock. At the exit of penstock, there is a nozzle. Through nozzle, high velocity jet is coming. Okay. Jet velocity will denote by capital V. Jet will be striking on bucket. At the splitter, it gets divided into two equal half part. When jet is traveling along this bucket, there is a change in direction. Due to change in direction, there is a momentum change and impact force is generated. The bucket will be traveling with velocity u. So definitely this u value has to be less than v, otherwise impact is not possible. If bucket is traveling faster than the jet, impact is not possible. So U value has to be less than V. So this value we will get by R into omega or pi dn divided by 60. Both are equivalent. R you can write d by 2 and omega 2 pi n by 60. This we are getting because this bucket is performing circular motion about axis of the turbine. Please remember, this is just cross-sectional view of a bucket. The bucket is traveling actually circular motion about axis of the turbine, and in circular motion velocity is equal to R into omega. Now let us discuss how to find out this jet velocity. If you remember our discussion, at the inlet of nozzle, energy is available in which form? Energy is available in two forms. One is pressure, because at this point pressure is more than atmospheric pressure. So energy head due to pressure is P by rho g. Again here energy is available in the form of kinetic energy, because this liquid will be having some velocity small v. V square by 2g. V square divided by 2g. Sum of these two energy is called which head? This is net head. So H is equal to P by rho g plus V square by 2g. This is net head. Same fluid, when it is coming here, whatever pressure available, that is getting completely converted into kinetic energy, because at exit pressure value is atmospheric pressure, which we consider 0. So there is no pressure energy. Whatever pressure energy which was available at inlet, that got completely converted in the form of kinetic energy. So if you use energy balance in between these 2 points, P by rho g plus V square by 2g at nozzle inlet. Okay, this energy is equal to energy at the exit of nozzle. Energy at the exit nozzle, only one head is available, that is kinetic energy head. So this is jet velocity, capital V jet velocity. Sum of these two, it is called net head. Am I right? So this complete term is net head. That's why we can write H is equal to V square by 2g. This we can write, of course, if there are no losses inside this nozzle. But whenever there is liquid which is flowing inside this nozzle, nozzle surface will offer some friction, and due to that friction, we'll get some loss. That loss we need to add on this side. So frictional loss inside nozzle. Please remember HF suffix n, this indicates loss inside nozzle. This is loss inside nozzle. Earlier we saw one relation. The relation was Hg is equal to H plus Hf. This Hf is different, this Hfn is different. This Hf is the loss inside penstock. This is loss in penstock. Please understand these differences. And Hfn is loss inside nozzle. Okay. So inlet energy is represented by net head. Exit energy is kinetic energy. If you consider loss, inlet energy is equal to exit energy plus loss. So here also we should add Hfn. So from this equation, we can write V is equal to root 2g H minus Hfn, which is equal to Cv into root 2gh. So this Cv will take care of Hfn. This is called nozzle velocity coefficient. Nozzle velocity coefficient. Hfn is very small value because nozzle length is short. So Hfn is small. So that's why the Cv value will be nearly equal to 1. So in real world problem, this value will vary from 0.95 to 0.99. This is range. No need to remember. These things will be given in the exam. The CV is called nozzle velocity coefficient. Please remember this formula. So whenever you want to find out jet velocity, use this formula. One of the important formula in the analysis of Pelton turbine. Now let us discuss very important concept of this velocity triangles. In the study of turbo machines, velocity triangle is central idea. Be it steam turbines, gas turbines, hydraulic machines, pumps, compressor, everywhere those velocity triangles are involved. And the fundamental of velocity triangles are same in all cases. It means if you are able to understand velocity triangle for any one machine, by analogy you can draw velocity triangles for all machines. Let us discuss velocity triangle for Pelton turbine now. In velocity triangle, there are mainly three velocities involved. That's why triangle. First velocity is absolute velocity of water. Second is relative velocity of water. And third is not jet, bucket velocity. Bucket velocity or blade velocity. These are three velocities. Please remember, V is absolute velocity of water. Absolute velocity means velocity of water with respect to ground. If you stand on ground and if you observe water, that is absolute velocity. Relative velocity of water means this is relative velocity of water and reference is bucket with respect to bucket or blade, you can say. It means if you stand on this bucket and if you observe the flow, whatever velocity you see, that is relative velocity. And third one is velocity of this bucket itself. To understand these velocity vectors, let us consider a very simple analogy. Let us say there is one bus. On the top of bus, one person is running. This bus is analogous to the bucket and the person is analogous to water. Velocity of this bucket it is u, this vector is u. Velocity of this person, either you can measure with respect to bucket or you can measure with respect to ground. So if you measure velocity with respect to bus, this velocity will be relative velocity. Velocity if you measure with respect to ground, some observer if he is standing here and if he is observing velocity of this person, velocity seen by this observer will be absolute velocity. Okay. So looking from the ground, among the person and the bus, who will travel faster, assuming that both the velocities are in same direction? Think for a while. You can pause video. Okay. See, bus is moving. On the top of bus, person is running. So if you observe from the ground, you will see that person is running faster. Why? Because after some time, this person has to overtake the bus. Am I right? He will overtake the bus. That's why person is running faster than the bus. You can think in this way also. Even though this person is stand still, still his velocity is not zero. Why? Because he is standing on bus. His velocity will be equal to velocity of the bus. On top of that, if this person starts running in the same direction, person will be having more velocity than bus. So absolute velocity of the person is equal to velocity of the bus, and into this velocity you have to add extra velocity which this person is possessing. Extra velocity is relative velocity. So this is the relation between these three velocities. Absolute velocity is equal to bucket velocity plus relative velocity. So this is very important relation. This I have taken very simple example. Here all three vectors are in same direction, but in our case vectors will be having different directions. So their complexity comes. But this identity will be true in all cases, whether these vectors have same direction, opposite direction, or some different directions. This identity will be true always. So you remember this. But while adding these vectors, you have to make you have to take one care. The care is while adding this vector, you should use triangle law of vector addition. I hope you know the triangle law of vector addition. Whenever first vector is ending, at that point you should start second vector, and the resultant vector will be starting at starting point of first vector and it is ending at end point of second vector. So this is A plus B. Am I right? So this is the triangle law of vector addition. So you have to use this law to add this vector. That's why velocity triangles are coming. Understood? Now let us start drawing different velocities. At inlet, jet velocity is V. So this V is absolute velocity of water at inlet. Buckets going in the same direction. So relative velocity from this equation, it will be difference between absolute and bucket velocity. So there is way to draw the velocity triangle. Please never mug up these velocity triangles. If you mug up, after some time you will forget. But if you draw these velocity triangles logically, you can remember those triangles for longer time. So whenever you want to draw the velocity triangle, first you always draw relative velocity. This vector you should draw first. Why? Because its direction will be known. The direction of relative velocity is always tangential to this bucket or blade at inlet as well as exit. Why? Because imagine that you are standing on this bucket. What you will see? You will see water is coming towards this bucket. At this point it is getting split and water is flowing along the curvature of bucket. So when this jet is leaving the bucket, it should leave tangentially. This is always true. Relative velocity at the exit is always tangential to the bucket profile, because with respect to this bucket, water does not have any direction to go. It cannot go in this direction or this direction. It has to follow the curvature. So there is physical restriction on the direction of flow. That's why this velocity has to be tangential. So this is relative velocity at exit. That's why VR2. Remember the notations: 1 for inlet, 2 for exit. At inlet, relative velocity is again tangential. So this is VR at inlet, that's why 1. And VR1 from this equation, both the vectors are in same direction. So this is V minus U. Understood? So draw these two vectors first. Once you draw relative velocity, to this relative velocity you have to add blade velocity by keeping in mind triangle law of vector addition. Okay. So relative velocity, I want to add blade velocity. You can add blade velocity either after or before. Anything is okay. As long as you are following triangle law, anything is okay. So I am adding here blade velocity before. So this is following triangle law. Wherever first vector is ending, second vector is starting. Absolute velocity vector will start at starting point of first vector. It will end at end point of second vector. So this entire vector is absolute velocity. So here I am showing this as a V. Clear? So inlet velocity triangle, in fact, it has collapsed to a line because all three vectors are in same direction. So there is no triangle, single line. Let us come to exit velocity triangle. Here first vector is ending. So second vector which I am going to add is bucket velocity. Bucket velocity vector I should add such that it is following triangle law. By the way, what is direction of bucket velocity? See, this is a cross section of a bucket. Entire cross section is moving towards right. So at all points velocity is same. Understood? This is a radial cross section. At a particular radius this cross section is taken. So everywhere velocity is same because R value is same. So add this vector U. Now resultant vector will be starting at starting point of first vector and it will end at end point of second vector. So this is resultant vector. At exit, that's why V2. Understood? So first you draw relative velocity. Relative velocity should be tangential to the bucket. At exit, why it is tangential? because flow does not have any direction to go. At inlet, it should be tangential to avoid entry shock. Let us understand this concept of entry shock. What happens if this relative velocity is not tangential? For example, this jet, it is not horizontal, it is slightly inclined, it is striking in inclined direction. So in that case, what happens is, let us say this is bucket. If jet is striking in this direction, so it is not tangential now, so you will get flow separation on opposite side. If it is striking on this direction, you will get flow separation on opposite side. So this VR is not tangential. That's why we are getting flow separation. This is called separation loss or entry shock. Entry should be smooth, relative velocity should be tangential, so that flow will be smoothly entering. To avoid this entry shock or separation loss, relative velocity has to be tangential. At exit, by default it will be tangential. You don't have to worry anything. At exit, flow is restricted to follow the curvature. That's why by default relative velocity at exit will be tangential. But at inlet, you have to take care. You have to align this nozzle direction in such a way that relative velocity is tangential. If you are not doing that, you will get entry shock or separation loss. Please remember this point. To avoid entry shock, relative velocity at inlet has to be tangential. At exit, there is nothing like exit shock. At exit, relative velocity is tangential because flow is forced to follow the curvature. That's why it is tangential. I hope you understand how to draw these velocity vectors. Now again, there are some angles. One is alpha, another is beta. Okay. This angle alpha is angle between absolute velocity and blade velocity, and beta is angle between relative velocity and blade velocity. For simplicity, you show all angles on interior side. This is the convention which I use, which is simple to remember. Different authors have different notations, but if you remember this trick, show all angles on interior side, you can draw velocity triangle correctly for all cases of hydraulic machines. Different authors have different notations. So angle between relative velocity and blade velocity, this angle is beta. At exit, that's why 2. Angle between absolute velocity and blade velocity, angle is alpha. At exit, that's why 2. Please remember, to measure angles, reference is blade velocity. All angles are measured with respect to this blade velocity, and simply show all angles on interior side, you will get correct angles. Let us discuss how to find out impact force on the bucket. The impact force formula is the most important formula in Pelton turbine. If you are able to find out impact force, from force you can find out torque. Torque is equal to force into radius, and from torque you can find out power. Power is equal to torque into angular velocity. So finding out this force is the most important, and it is easy to find also. I will tell you the technique. Before that, let us understand the different velocities here. As we have discussed in the velocity triangle, there are 3 velocities: relative, absolute and bucket velocity. What is absolute value of water at inlet? At inlet, absolute velocity is equal to jet velocity V. Let us imagine that this bucket is not moving, this bucket is fixed. Okay, so U value is 0. Inlet velocity of water will be V. In case of fixed bucket, it is V. What will be the exit velocity at this point? Think. You can pause video and think. Okay. Inlet velocity and exit velocity, ideally they should be same. This velocity also has to be V if bucket is fixed. This also has to be V if bucket is fixed. Why? What is the value of pressure here? Atmospheric pressure. At exit, again atmospheric pressure. You can apply Bernoulli's equation between these 2 points. So as per Bernoulli's equation, if pressure is same, and if elevation is also same, velocity has to be same. Remember, this cross section is taken in horizontal plane, so this elevation is same. Pressure is also same, so this velocity has to be same. But in reality, due to friction, this velocity slightly reduces, and that becomes some k times of v. K is called bucket friction coefficient. This k is bucket friction coefficient. Its value will be again nearly equal to 1. You will get it 0.9 to 0.98 bucket friction coefficient. Now let us consider case of a moving bucket. When the bucket is moving, in that case, you imagine that you are standing on this bucket. When you are standing on the bucket, you will see bucket as a stationary, so it should behave like a stationary bucket. When you are standing on the bucket, you will see relative velocity let v minus u, because both are going in same direction, so relative velocity will be difference between jet velocity and bucket velocity. So you will see the at inlet water is coming with velocity equal to relative velocity. In ideal case of fixed bucket, absolute velocity will remain same. Whenever you are moving along with this bucket, you will see bucket as a stationary, and for stationary bucket, velocity has to be same. So this velocity has to be again v minus u. But due to friction, it gets reduced. So Vr2 becomes k times Vr1, and Vr1 is v minus u. Please remember this point. In case of Pelton turbine, inlet relative velocity and exit relative velocity both are almost same. There is slight decrease due to friction. This we conclude from Bernoulli's equation, and this result is true only for Pelton turbine. If there is a Kaplan turbine or Francis turbine, don't take Vr1 equal to Vr2. Those are not nearly same, okay, because that flow happens in a closed conduit. In closed conduit, if area changes, velocity will change. This flow is happening in an open space, so this jet area is almost same, so that's why relative velocity remains same. This result is not true for other turbines. So K is bucket friction coefficient, so this K value is defined as ratio of Vr2 and Vr1, okay. Apart from this relative velocity, the jet which is going at exit, it will be having additional velocity, and that velocity is equal to bucket velocity. See, if you stand on the bucket, you will see jet is going in this direction. If you stand on ground, you will see that this bucket is not fixed. Bucket is moving towards right with velocity equal to u. Velocity observed from the ground will be vector sum of these velocities. You can see this picture. There are two velocities at exit. One is relative velocity, another is absolute velocity. If you observe, the relative velocity is tangential to the bucket, and it must be, because if you stand on ground, whatever velocity you will see, that is absolute velocity, and if you stand on bucket, whatever velocity you see, that is relative velocity, okay. Imagine that you are standing on bucket, so you should see water going tangential to the bucket. And if you stand on the ground, the water will be having additional velocity to the relative velocity, that is bucket velocity, because along with this bucket, water is going towards right. That's why if you take picture of a flow inside a bucket of Pelton well from ground, everywhere you will see absolute velocity, and you will see this kind of picture. So at exit, you will see water is going along absolute velocity if you observe from the ground, and if you observe from the bucket itself, you will see water is going along relative velocity. So this picture, you can say it is taken from ground. What I was talking is, at the exit of this turbine, there are two velocities based upon the reference. One is relative velocity. If you stand on this bucket, you will see relative velocity, and it is tangential to the bucket. If you stand on the ground, you will see the absolute velocity, Absolute velocity is vector sum of this relative velocity and bucket velocity. So that's why observing from ground, this jet will go in this direction. Now come to this derivation of force. Force is equal to mass striking per unit time into decrease in velocity. This is in fact Newton's second law. Force depends upon two things. One is mass striking and another is change in velocity. This formula you can use in case of free jet. What is meaning of free jet? When jet is exposed to atmosphere. So in all such case you can use this formula, be it flat plate, fixed flat plate, moving flat plate, curved vane, moving curved vane. In all cases you can use this formula. So force depends upon two things. One is mass striking on the bucket. Second is how much velocity is changed. Mass striking into change in velocity, it will represent momentum change. And if you take mass striking per unit time, it is rate of change of momentum. And as per Newton's second law, that has to be equal to force. Now come to this mass striking part. Let us first discuss mass striking in case of single bucket, and second is in case of multiple buckets. Single bucket and multiple buckets. Our case is Pelton turbine which is having multiple buckets. So first we will discuss single bucket. Okay. Imagine there is only one bucket. So mass striking depends upon relative velocity when there is a single bucket. Let us see why. Imagine that both jet and bucket are having same velocity. In that case, what should be the value of mass striking? It should be 0. Why? Because as jet and bucket both are having same velocity, jet will not be able to catch the bucket. Always there will be gap between these two. Both will be moving with same velocity. So mass striking is not possible. In order to strike this jet on bucket, absolute velocity must be greater than bucket velocity. Then only striking is possible. And mass striking will depend upon difference between these two velocities. That's why for single bucket, mass striking is rho A into VR1. This is mass striking per unit time. If there are multiple buckets, then instead of VR1, we should take absolute velocity of jet. And this is the major difference. Please remember this. Instead of relative velocity, you have to take absolute velocity. Let us see why. If there is a single bucket, then nozzle is fixed, bucket is moving. So always gap between nozzle and this bucket will keep on increasing. Am I right? So out of mass coming out of this nozzle, some mass will be stored inside this gap, and this gap will keep on increasing. So there will be always some storage of mass between nozzle and bucket. But if there are multiple buckets, then if one bucket moves, immediately next bucket will take its place. If second bucket moves, third bucket will take its place. So this gap will be same. So there will not be any storage. In other words, you can say that whatever mass coming from this nozzle, it will strike on any one of the bucket. So on an average, mass striking per unit time will be equal to rho A V instead of rho A VR1. Please remember this point. So here we can write mass striking per unit time is rho A V. Now let us see how to find out this difference. Difference in which direction you have to find out? Difference in the direction of impact force. So impact force will be acting at this point. Okay. So in horizontal direction we should find difference. Initial velocity before impact is V. Okay. So either you can find out this difference in absolute frame or relative frame. It's okay. In both cases you should get same answer. Now I am finding this difference in absolute frame. In absolute frame, inlet velocity is V and it is in horizontal direction. Minus at exit, in absolute frame, absolute velocity is vector sum of these two velocities. So we should consider either x component of absolute velocity, or you take x component of VR2 and u and then take their sum. Both are equivalent. So x component of u is u, x component of VR2, it will be negative, so minus. If you remember the velocity triangles, this angle will be beta 2, angle made by relative velocity with bucket velocity, that is beta 2. So x component of this VR2 will be VR2 cos beta 2. This is equal to rho a v minus u, minus will get plus VR2 cos beta 2. Now if you find out this difference, this decrease in velocity in relative frame, again you should get same answer. Let us discuss in relative frame. In relative frame means, imagine that now you are standing on the bucket, then at inlet you will see relative velocity, and that velocity is v minus u, so that's why v minus u here. At exit you will see relative velocity VR2, and it is in backward direction, so its x component will be minus k v minus u into cos beta 2 for x component. So minus it becomes plus here, so you'll get exactly same answer. Either you take this difference in absolute frame or relative frame, you should get same answer. This you can simplify, rho a v minus u, and this VR2 you can write k times VR1, and VR1 is v minus u. So k times of v minus u cos beta 2. So f is equal to rho a v minus u into 1 plus k cos beta 2. This is most important formula in Pelton turbine. In fact, if you remember this formula, no need to draw velocity triangles. All the questions, almost all the questions you can solve directly using this formula. By using force you can calculate torque, by using torque you can calculate power, and so on. So please remember this formula. If you know the force, from force you can calculate torque. Torque exerted by jet on runner. Okay, so torque is equal to force into radius. The formula for force is rho a v into v minus u 1 plus k cos beta 2 into r. So this is formula for torque. So once you know torque, you can calculate power. Power generated by runner. Okay, now onwards I will use short notation RP. RP means you can consider runner power or rotor power. So rotor power is equal to torque exerted on rotor into angular velocity. Am I right? Power is equal to either force into velocity you can take, or torque into angular velocity. Both cases you should get same answer. So torque is rho a v minus u 1 plus k cos beta 2 into r into omega. What is this r into omega? R into omega is velocity. Which velocity it should be? It should be bucket velocity, because this is angular velocity of a bucket. So u. So you'll get formula for runner power is equal to rho a v into v minus u 1 plus k cos beta 2 into u. This is another formula. No need to remember this formula separately. Either you can calculate this formula by torque into angular velocity, or directly this first part is force into velocity. So this is also okay. Torque is equal to F into U. Let us discuss now concept of wheel efficiency. Wheel efficiency, it is denoted by eta suffix W. Now how it is defined? Observe this diagram. In the diagram, what is input energy to the Pelton wheel? You can observe in the diagram, jet is striking on the bucket. So kinetic energy of jet is the input energy. So this should be in denominator. What is output of Pelton wheel? Output of Pelton wheel is mechanical work. Okay, we are getting shaft work. So this mechanical work output is nothing but runner power or rotor power. So ratio of runner power and kinetic energy per unit time, that is wheel efficiency. Please remember these notations. Ke does not mean simply kinetic energy. Ke means kinetic energy per unit time. So Ke equal to kinetic energy per unit time. For simplicity, I'll use this notation. Every time I'll not write per unit time, per unit time. So Ke means kinetic energy per unit time. Wheel efficiency. Wheel efficiency is equal to runner power divided by kinetic energy. We have derived the formula of runner power. So this is rho A V, V minus U, 1 plus K cos beta 2. This is formula for force. Force into bucket speed, you will get runner power divided by kinetic energy formula is 1/2 mv square. But in denominator we have kinetic energy per unit time. So instead of m, we should take m dot. If you observe the numerator, this rho A V is nothing but mass flow rate. So this and m dot, it will get cancelled out. So you can write wheel efficiency formula eta W equal to, this 2 will go up. So U I am writing first, V minus U 1 plus K cos beta 2 divided by V square. So this is formula for wheel efficiency. Okay, no need to remember this formula separately. Only formula which you have to remember is force formula. From force, you can quickly calculate power. Power divided by kinetic energy, you will get wheel efficiency. Now observe these parameters. Wheel efficiency is function of U, V, K, beta 2 and V. Out of those parameters, few parameters we can control, few are beyond our control. For example, bucket friction coefficient K. Friction we cannot control, so this is not in our control. See this jet speed, the formula of jet speed V is equal to CV into root 2 GH. Jet speed depends upon net head, and net head depends upon water available in the dam. Water available, level of water available in the dam, that also we cannot control. So this is also not in our control. So for a given net head, you will get some jet speed. So this is not a variable. Beta 2, what is beta 2? Beta 2 is bucket angle. Now turbine buckets we can manufacture as per our wish, but once turbine bucket is manufactured, this beta 2 is beyond control. Okay, once turbine bucket is manufactured, beta 2 we cannot control, it will be fixed. So for a given Pelton wheel, only parameter which we can control is U. U is bucket speed, this we can change. So that's why this wheel efficiency is function of U. Let us now discuss condition for maximum wheel efficiency. We have derived the formula of wheel efficiency as eta W is equal to 2 times of U, V minus U, 1 plus K cos beta 2 divided by V square. And we have also discussed that this wheel efficiency is function of only bucket speed, because V, K, cos beta 2 for a given turbine, these are beyond our control. These cannot be varied. So wheel efficiency is function of U. And in the mathematics, we have seen that if function has a maxima, then its derivative has to be 0. Therefore, for maximum value of wheel efficiency, the condition is derivative of this wheel efficiency must be 0. So this derivative is 0. Now from here, if you see v k cos beta 2, it is constant, only u is variable. So constant parameters will take out. 2 into 1 plus k cos beta 2 divided by v square d by du of u into v minus u square, this is equal to 0. So derivative of uv is v, derivative of u square is 2u, this is equal to 0, or u is equal to v by 2. So this is very popular condition. Many times question is asked based upon this condition. The condition says that for maximum wheel efficiency, bucket speed must be half of jet speed. Okay, so in that case you will get efficiency maximum, and the corresponding value of this maximum efficiency we can get by keeping u is equal to v by 2 in this equation. To get value of maximum efficiency, we will substitute u is equal to v by 2 in this equation. So we will get 2 u value is v by 2, u value is v by 2, 1 plus k cos beta 2 divided by v square. This 2 will get cancelled, v square will get cancelled. So what we will get is 1 plus k cos beta 2 divided by 2. So this is maximum value of wheel efficiency. Okay, and for that condition is u must be equal to v by 2. This is the condition. Now we can discuss the variation of this wheel efficiency versus u. So let us draw the graph. On x axis we will take u, and on y axis we will take wheel efficiency. Let us see now. When u value is 0, entire term becomes 0, so you will get 0 efficiency. What is the maximum possible value of bucket speed? The theoretical maximum possible value of bucket speed is equal to jet speed. Bucket cannot run faster than the jet, am I right? So that is why maximum possible value of u is v. If you substitute u is equal to v, then again you will get wheel efficiency is 0. At u is equal to v, you won't get any impact. At u is equal to v by 2, wheel efficiency is maximum, and we will get some variation now. This maximum value is 1 plus k cos beta 2 divided by 2. This is the maximum value. This is the variation of wheel efficiency. Now there is overall efficiency also. We will discuss what is overall efficiency later in detail. For the time being, you can understand overall efficiency is just your minimum possible efficiency of a turbine. So this is having minimum value. Wheel efficiency will be having slightly higher value. Overall efficiency will consider all losses. So variation of overall efficiency will also be similar, but as overall efficiency is less than wheel efficiency, the graph will be below this curve. So I will draw that graph by dotted curve. Something like this. So initially it will follow closely. It will peak little bit earlier, and at the end there will be some difference. So this is for overall efficiency. and this curve is for wheel efficiency. Okay, so overall efficiency will peak at a slightly less value than V by 2, maybe around 0.45 V by 2 to 0.48 V by 2. At that value, overall efficiency will peak. Okay, now let us discuss significance of this point. Okay, what does this point indicate? U is equal to V means bucket speed is equal to jet speed. So at this point, we will get theoretical maximum possible value of a bucket speed, and the corresponding value of runner speed is called runaway speed. Runaway speed is indicated by NR. NR is the highest possible value of turbine speed. When we will get this value? When turbine is running under no load condition. Let us imagine that you have disconnected that turbine from a generator. There is no load on the turbine and jet is striking on the turbine. So what that jet will do? It will try to rotate the turbine at highest possible speed, and that speed is called runaway speed. So theoretical possible value of bucket speed is equal to jet speed. That's why this is theoretical runaway speed. Actual runaway speed will be corresponding to this point. So this is actual runaway speed. Remember this point, runaway speed is maximum possible speed of a turbine which can be achieved under no load condition. Notice practical significance of this runaway speed. Whenever you are designing turbine, you should design turbine corresponding to runaway speed, because at runaway speed stresses will be the maximum. Turbine will be rotating at highest speed, so stresses will be maximum, and turbine should withstand this runaway speed, because by chance some accident happens and turbine gets disconnected from the generator. In such situation, turbine will run at runaway speed and it should be able to withstand. So this is physical significance of runaway speed. Let us discuss now various efficiencies. As discussed earlier, input to the turbine is considered as net head. Net head is head available at the inlet of nozzle, and here energy is available in which form? Here energy, if you recall, energy here is available in the form of pressure energy and kinetic energy, and both together are expressed by net head. Okay, so this is considered as an input to the turbine. The final output of the turbine is considered mechanical power, which is also called shaft power, which is transferred to the generator. That is considered as a final output. In between those energy conversion processes, there are various losses at each stage. Now let us discuss one by one different losses. When water is flowing through this nozzle, the nozzle friction, there will be some loss. Okay, and that loss is accounted by CV, coefficient of velocity. The nozzle output is kinetic energy, and at the inlet of nozzle is energy of a fluid, which is represented by net head, and this energy is called hydraulic power. This is discussed. The formula of hydraulic power is rho g QH. So input to the nozzle is hydraulic power, output to the nozzle is kinetic energy. So first block, this must be hydraulic power. Each block represents some energy. So highest possible energy is hydraulic power, which is power present at nozzle inlet. During the processes, in each stage there will be some losses. In nozzle, there will be nozzle frictional loss. If you subtract that loss, the remaining power here is kinetic energy per unit time. So this is represented by Ke. Remember, Ke indicates kinetic energy per unit time. This we have discussed earlier also. Then kinetic energy is striking on K. Out of that kinetic energy, entire kinetic energy will not be converted into mechanical work, because there are different losses. The power generated by this runner, torque into angular velocity, that is called runner power or rotor power. Whatever power is generated by rotor, entire that power is not transferred to the generator, because there are some mechanical losses. Let us imagine that this turbine is driving the runner. Okay, turbine is driving the generator, and imagine that on one side of, let us say this is of a turbine. On one side of this shaft there is a turbine wheel, on another side there is a generator, and turbine is driving the generator. So on the shaft there will be some bearing frictional loss. So due to that, whatever turbine power is generated by turbine, that is not transferred to the generator. There is another loss called windage loss. Windage loss means aerodynamic resistance to the wheel. When this Pelton wheel is running, it is running at ambient conditions. So air will offer some resistance, that is called windage loss. Due to these two losses, entire power generated by this runner is not transferred to the generator. The final power which is transferred, it is called shaft power, SP. This is final output given to the generator. Okay. So now let us write different losses. The difference between runner power and shaft power, this is mechanical loss. Okay. Difference between hydraulic power and kinetic energy, this is nozzle loss, nozzle frictional loss. Okay. Now let us think. You can pause video and think what should be the difference between kinetic energy and runner power. This I am writing this as number 2. Okay. So what should be this number 2 loss? You can pause video and think. Okay. Now let us discuss. Kinetic energy is striking on this bucket. Entire kinetic energy is not converted to the mechanical work. One of the loss is bucket frictional loss, but that is not a major loss. Here the major loss is the kinetic energy loss at exit of this bucket. When the water is striking on the bucket, after striking, water will be going into the tail race, and the water which is going in the tail race, it will also have some kinetic energy. Am I right? It will also have some velocity. If you remember velocity triangle, at exit there is absolute velocity vector v2. Yes or no? So this absolute velocity vector v2 we are not going to use. That velocity is as it is going in tail race, and this accounts for a major loss. Okay. So point number 2 represents exit KE loss, exit KE loss, and bucket frictional loss. Okay. So these are the various losses, and various efficiencies will take account of those losses. For example, between these two we defined nozzle efficiency. Between runner power and kinetic energy, here we defined wheel efficiency, and this one will be the mechanical efficiency. Mechanical efficiency considers mechanical losses. One more thing, one term is used, hydraulic efficiency. Now let us discuss what is that hydraulic efficiency. Many people will have confusion in between wheel efficiency and hydraulic efficiency. The hydraulic efficiency considers hydraulic losses. Hydraulic losses means losses which are related to water. See, nozzle frictional loss, it is related to water. Second loss, exit kinetic energy loss, this is also related to water, and bucket friction loss, this is also related to water. So number 1 and number 2, all those losses are related to water, and those are called hydraulic losses, and the efficiency which considers hydraulic losses is hydraulic efficiency. So between runner power and HP, hydraulic efficiency is defined. The mechanical efficiency considers mechanical losses. Mechanical loss means which loss? This means bearing friction, and windage. What is meaning of windage? Windage loss means aerodynamic resistance to the wheels. So those losses are considered in mechanical losses. I hope you understand these various losses. Now let us discuss nozzle efficiency. The nozzle efficiency, look from this diagram, nozzle efficiency considers losses in nozzle. Output of nozzle is kinetic energy, input is hydraulic power. So nozzle efficiency is equal to kinetic energy per unit time divided by hydraulic power. The formula for kinetic energy is 1/2 mv square. and if you find kinetic energy per unit time, then it is m dot you have to take. Hydraulic power is rho g q a. So m dot is rho into q. So this is also equal to v square by 2g divided by h, because rho into q is m dot. So kinetic energy head is output in terms of head, and net head is input to the nozzle. We have seen the formula velocity. Jet velocity is equal to c under root 2gh. Its square, the denominator is h, divided by here 2g is there. So 2g will get cancelled, h will get cancelled, so we'll get cv square. So nozzle efficiency is simply equal to cv square. Remember this formula. This is very handy. Mostly in the questions, velocity coefficient will be, so directly you can find out nozzle efficiency as cv square. Then we'll discuss mechanical efficiency. Mechanical efficiency eta m. We already discussed wheel efficiency. Now only we will discuss mechanical efficiency. Mechanical efficiency will consider mechanical loss. Okay. So mechanical loss is difference between runner power and shaft power. So RP minus SP is equal to mechanical loss. And what is meaning of mechanical loss? Losses which are not related to water. So we'll get here bearing friction plus windage. These are the mechanical losses. Okay, and mechanical efficiency is defined as mechanical efficiency is equal to SP divided by RP. SP is power transferred to the generator and RP is power generated runner. So this is work developed, and output represents actual useful work, because some of the work developed is lost in bearing friction due to various mechanical losses, bearing friction and windage. I hope you understand these different losses in the Pelton turbine. Let us discuss hydraulic efficiency now. Hydraulic efficiency, it is denoted by eta suffix h, hydraulic efficiency. As we discussed earlier, hydraulic efficiency is related to the hydraulic losses. Hydraulic losses means losses which are related to water. Nozzle frictional loss, it is related to water. Second loss, this is kinetic energy loss plus bucket friction loss. This is also related to water. So hydraulic efficiency eta h, it is defined as runner power divided by hydraulic power. We should include all hydraulic losses. This you can rearrange as kinetic energy divided by HP into runner power divided by kinetic energy. Okay. So kinetic energy by HP, what does this represent? This represents nozzle efficiency, and runner power divided by kinetic energy, this represents wheel efficiency. So that's why hydraulic efficiency you can write as a product of nozzle efficiency and wheel efficiency. Similarly, we'll discuss overall efficiency. Overall efficiency. Overall efficiency, it is denoted by eta suffix O. Overall efficiency considers all losses. So final output which is transferred to the generator is shaft power, and initial input supplied to the nozzle is hydraulic power. So overall efficiency is ratio of SP divided by HP. This also you can rearrange as kinetic energy divided by HP into RP divided by kinetic energy into SP divided by RP. Am I right? So overall efficiency is equal to, first term is nozzle efficiency, second term is wheel efficiency, and last term is mechanical efficiency. Product first two is hydraulic efficiency into mechanical efficiency. So this is formula for overall efficiency. We'll discuss those terms. First term is jet ratio. Jet ratio, it is denoted by M. This jet ratio is defined as wheel diameter ratio of wheel diameter to jet diameter. Okay. So M is equal to capital D divided by small d, ratio of wheel diameter to jet diameter. Wheel diameter means runner diameter, jet diameter means at the nozzle there is a jet, so diameter of that jet. Another term is called speed ratio, very commonly used term, speed ratio. It is denoted by Ku. Speed ratio is defined as U divided by root 2 GH. U is bucket speed, root 2 GH. This root 2 GH, this is theoretical jet speed. Some author slightly define speed ratio differently. So instead of theoretical jet speed, they will take actual jet speed. But I'll follow the convention which is used in K. Subramanya. In that book, it is defined as bucket speed to the theoretical jet speed. And one advantage of this definition is valid for all turbines. Same definition you can use in case of Francis turbine as well as Plum turbine. But if you take U by V, this definition you cannot use in other turbine. So you can say this approximately is equal to U by V, where V is actual jet speed. Why approximately? Because there is a difference between actual and theoretical jet speed by factor of CV. So there is another term, actually another formula for number of buckets on wheel. Z, number of buckets. These are the buckets. Okay, these buckets should not be too less. Let us say there are very less buckets. Let us say only 4 buckets. So what will happen in that case? If number of buckets are very less, so by the time next bucket reaches in front of this jet, some water will be lost. So you will not be utilizing all the water. That's why number of buckets should not be too less. If number of buckets are too many, like this, what will happen? If number of buckets are too many, then water deflected by this, it will be striking on back side of upcoming bucket. It will be striking on back side, and this is not desirable thing. If water is striking on back side, then it will generate negative torque, which is not desirable. So that's why number of buckets should not be too many also. So optimum number is obtained through experimentation, and it is given by empirical formula. This is will. Z is equal to 0.5 into M plus 15. So minimum number of buckets is 15. So 15 plus 0.5 into M. M is jet ratio, D by D. This is called Taigun's formula. Taigun's formula. This is empirical relation obtained through experimentation. You might be knowing the turbine must run always at constant speed. You should not run turbine at different speeds, and there is practical significance for that. We will discuss that now. Let us consider basic diagram of a generator. You might have studied generator in your school. So generator consists of north and south pole. Inside that some winding will be rotating, and due to rotation of this winding, electric current is generated. Okay, we will not go into the details of generator, but this generator, it is driven by what? It is driven by turbine runner. Faster the turbine runs, faster this generator will also run, and faster the AC will be produced. You can think in this way: one revolution of runner, it is equivalent to one cycle of AC. One revolution of this generator, it is equivalent to one cycle of AC. When this generator rotates by one revolution, you will get one cycle of AC. If it is rotated faster, you will get faster cycles of AC. You might have studied AC will be having cycles, right? Sinusoidal cycle. So one revolution is equivalent to one cycle. If turbine is running at n RPM speed, n RPM means n revolutions per minute. So in 1 second there will be n by 60 revolutions. Am I right? In 1 second there will be n by 60 revolution, and this many number of AC cycles will be produced. So frequency of AC will be equal to n by 60. But there is one variation also. This is true if there is only one pair of north and south pole, but around the generator, let us see this side view of generator. Around the generator you can have different pairs of poles like this. Different pairs of north and south pole. One pair is here, another pair will be here, something like that. So as you increase number of pairs, number of cycles will also increase proportionately. So F is equal to Pn divided by 60. P is pairs of magnetic poles. Pairs of magnetic poles of generator. Okay. So faster the speed, higher will be the frequency. And you might be knowing, in India, frequency of AC is 50 Hertz, and frequency we should maintain, because all electronic devices, those are designed by taking account of this frequency. These are designed for 50 Hertz frequency. If there is a variation in frequency, then definitely those electronic devices will get damaged. Electronic devices like TV, laptop, those devices will get damaged because those are designed for this frequency. To maintain constant frequency, we should run this turbine at constant speed only. That's why governing comes into picture. The governing is process of maintaining the turbine at constant speed. We'll discuss this governing aspect later, how governing is done in different turbines. But whole idea of this governing is to maintain constant speed so that frequency of AC will remain constant. Hello everyone, look at this question. This is simple question asked on Pelton turbine. I am reading the statement now. For a Pelton wheel with a given water jet velocity, the maximum power output from the Pelton wheel is obtained when the ratio of bucket speed, the meaning of this bucket speed is U, to the water jet speed. Water jet speed means V. Now this is very standard condition. For maximum power as well as for maximum efficiency, we have derived the condition. For maximum power or efficiency, what is condition? Yes, we derived this condition. U by V equal to 1 by 2, that is 0.5. So this is very simple question, and this is very standard result. Many times in GATE as well as ESE, question based upon this concept is asked. Please read this question. Statement is quite lengthy. This question was asked in GATE 2008 in mechanical engineering. EME 2008 for 2 marks. This question is actually from my paper. Water having density 1000 kg per meter cube issues from a nozzle with velocity. So V is given. So this is V. And jet strikes a bucket mounted on a Pelton wheel. The wheel rotates at 10 radian per second. Omega is given. Mean diameter is given. the jet splits into two equal streams by the bucket such that each stream is deflected by 120 degree as shown in the figure. The friction in bucket may be neglected. Magnitude of the torque exerted by water per unit mass flow rate of the incoming jet is, okay. So here diagram is also given. So incoming jet is deflected by 120 degree. Now here jet deflection angle, that is theta, we measured with backward direction, right? So theta we measure with backward direction. So theta here is 180 minus 120, that is 60 degree. What is asked in the question? Torque per unit mass flow rate, that is torque divided by m dot he is asking. What is formula for torque for Pelton turbine? So as I mentioned during theory, all the formulas for Pelton turbine, remember, if you remember the formula for impact force. So torque is equal to impact force into radius. Impact force equal to rho a v into v minus u into 1 plus k cos theta, and r is d by 2, correct? This rho a v is in fact, this is mass flow rate. He is asking torque per unit mass flow rate. Therefore, torque divided by m dot, we will get v minus u into 1 plus k cos theta into d by 2. Substitute the values now. V is jet velocity is 10 per second. This u is bucket velocity is equal to I into omega, am I right? Diameter is 1 meter, so r is 0.5 and omega is 10. So this is equal to r into omega, right? U is equal to r into omega. Bucket is performing circular motion. In circular motion, velocity is equal to radius into angular velocity into 1 plus k. Now think carefully and tell me what is value of this k. K is bucket friction coefficient. In the question it is mentioned bucket friction may be neglected. Bucket friction is neglected, so don't take this k equal to 0. Bucket friction is neglected. In that case, k value is 1 because k is defined as VR2 divided by VR1. VR2 divided by VR1. Due to bucket friction, there is slight reduction in relative velocity. That's why VR2 will be slightly less than VR1. But if you neglect bucket friction, then VR2 and VR1 will be same. In that case, k value will be 1. So 1 into cos 60 into d by 2 is 0.5 or 1 by 2 can. D is 1 divided by 2. If you perform these calculations carefully, you will get answer 3.75 Newton meter per kg per second. So answer is D. Hello, read this question. This is quite difficult question. It was in civil engineering 2016 for 2 marks. You can pause the video and you can read the question. Try to understand the given data. So first here I am listing the given data. A penstock of 1 meter diameter and 5 kilometer length is used to supply water. So penstock diameter dp is given 1 meter and length of penstock is given 5 kilometer. Okay. Nozzle diameter is given here 15 centimeter. So nozzle diameter we indicate by small d, 15 centimeter. Okay. Elevation difference between the turbine and water level in the reservoir is 500 meter. So what is this 500 meter? Yes, net head or gross head. It is not head available at the inlet of nozzle. It is the elevation difference between free surface of water in reservoir and tail race level. So that means it is a gross head. Gross head is given. This is important point. Gross head is given 500 meter. Consider head loss due to friction as a 5% of velocity head available at the jet. So HF is given 0.05 times of V square by 2g. Specific weight of water is given, acceleration due to gravity is given, so G value is 10. G value is 10 meter per second square, and overall efficiency of the turbine is given 80%. What we have to find? Power generated expressed in kilowatt. Okay, power generated means some power you have to find out. Now the question is, which power you have to find out? Shaft power or hydraulic power? Yes, you can pause the video and you can think which power you have to find. See here, overall efficiency is given, and this overall efficiency, it is related to SP, right? Overall efficiency is equal to SP divided by HP. As this overall efficiency is given, we must find shaft power. Instead of overall efficiency, if they give hydraulic efficiency, in that case we can find rotor power. Okay. Fine. Now what is formula for shaft power? Shaft power is equal to overall efficiency into HP. So overall efficiency, and this HP is nothing but rho GQH, right? So SP is equal to overall efficiency into rho GQH. Now in this equation, overall efficiency is known, rho G is known, Q and H both are unknown. First, we'll try to find out this H. The given head is gross head. The relation between gross head and net head is gross head is equal to net head plus HF. This gross head is given 500. Net head we have to find, and this HF is equal to 0.05 times V square by 2g. Still, in this equation there are two unknowns. Somehow we have to relate this head and velocity. You can think, you can pause this video for a while and tell me how to relate this H and velocity. Some of you may be correctly identifying this. V is equal to CV times root 2gh, right? CV times root 2gh. This is relation between head and velocity. Now substitute value of V in terms of H. So 500 equal to H plus 0.05 divided by 2g into CV square into 2gh. Okay, V is equal to CV into root 2gh. Take a square, so CV square into 2gh. Okay, so this 2g and 2g will get cancelled out. CV is not given here. You can read this given data. Nowhere CV is mentioned. But this CV value is very nearly equal to 1. So we can approximate this as a 1. So from here, 500 is equal to what you are getting? This 500 is equal to H plus 0.05 times H. So I am writing this on the next slide. $500 equal to H plus 0.05 times H. So this H is equal to 500 divided by 1.05. So you will get this as 476.2 meter. Okay. Now in this equation, now H is known. Discharge we have to find out. How to find out discharge? Discharge equal to area into velocity. Area is equal to pi by 4 into d square, and velocity is equal to CV times of root 2gh, right? So this is area and this one is velocity. Now substitute the values. Pi by 4 into 0.15 square into, okay, CV is 1 into 2 into 10 into H is 476.2. If you do these calculations carefully, you'll get discharge around 1.724 meter cube per second. Okay. Now SP. See here, in this equation now everything is known. SP is equal to overall efficiency into rho g QH. Overall efficiency into rho g QH. Substitute the values now. Overall efficiency is given 80%, that is 0.8, rho is 1000, g is 10 into Q is 1.724 into H is 476.2. If you do these calculations carefully, you'll get answer 6569 kilowatt. Okay, so this is the answer. Now let us understand working of the Francis turbine. Francis turbine is reaction type of turbine. First, let us understand various components and how water flows in the turbine. See here, this is water intake from penstock. So up to penstock, everything will be same like Pelton turbine. From reservoir, water will be carried through a penstock. In Pelton turbine, at the end of penstock, there was a nozzle. Now here there is no nozzle. At the end of penstock, there is a casing, and this casing is having gradually decreasing area. So this casing is called spiral casing. Okay. So this is spiral casing. It is having gradually decreasing area. White's area is decreasing, that we will see later. First you understand various components. In the side view, you can see this casing here. Here cross-sectional area is big. On this side, cross-sectional area is less. So cross-sectional area is gradually decreasing. So after casing, there are guide vanes. Okay. So there is big thick aerofoils. You are seeing those are guide vanes. In this view, guide vanes are shown here. Okay. I have few more cut sections. Yeah, you can see here. See, this is guide vane. These are kind of aerofoil sections. Okay, so these are guide vanes. Okay, so after guide vanes, there is a runner. You can see here. So this is a mechanism which tilts guide vane. So this guide vane are tilted. What is their function? Later on we are going to see in detail. First you understand various components. So after spiral casing, there is a guide vane. After guide vane, there is a runner. Okay, so this is a runner. Okay, so in this diagram you can see, yeah, this one is the actual photograph of runner. Runner of a turbine can be very big. Here it's shown in red color. So this is runner. Runner is a rotating component, that's why it is called runner. Guide vanes are stationary component. So after runner, water leaves axially into the draft tube. Okay. So you can see in this view here, this is a sectional view. So after guide vane, water enters into the runner. After runner, water enters into the draft tube. After draft tube, water enters into the tail race. Tail race is low level reservoir. So these are the various components. First is spiral casing, then guide vanes, then runner, and then draft tube. So these are the components. Water flows from penstock to casing, casing to guide vane to runner, and runner to the draft tube. Now understand function of various components. First we'll see spiral casing. First component is spiral casing. So basic function of the spiral casing is to distribute water equally to all guide vanes. Okay. So what I am saying is, from spiral casing, water is entering into the guide vane. So here water is entering. So everywhere water should enter equally, so that turbine will be loaded symmetrically from all sides. If water is not coming equally, then turbine will not be loaded symmetrically from all sides. There can be problem of vibration. So function of this casing is to distribute water equally to all guide vanes. Now how this function is performed? What this spiral casing basically does is, it maintains equal pressure and velocity at the inlet of each guide vane. Similar condition it is maintaining. It will maintain same velocity everywhere. So if I take various points here at the inlet of guide vanes, so each of this point, it will have same velocity as well as pressure. So as the flow conditions are symmetric at the inlet of each guide vane, discharge taken by the guide vane will be same. Now how pressure and velocity is maintained constant? See here, the discharge through the spiral casing, discharge passing through the spiral casing in this direction, it is gradually decreasing. Why it is gradually decreasing? Because some amount of this discharge is taken by each of the guide vane. So let us say total discharge 100 is coming, out of which 5 discharge is taken by first guide vane, 5 discharge will be taken by second guide vane, and so on. So outgoing discharge will be first 90, 90, 85 and so on, like this. So gradually discharge through the spiral casing will be decreasing. The formula for discharge equal to area into velocity, right? Area into velocity. Discharge equal to area into velocity. This discharge passing through the spiral casing is decreasing because some amount of the discharge is taken by each guide vane. I need to maintain this velocity constant. Inside the spiral casing, I need to maintain velocity constant. Because in this passage, same flow condition I need to maintain. Everywhere I need to maintain same velocity and same pressure. So velocity I need to maintain constant. So what we do is, we will decrease this discharge proportional to the discharge. We will increase this area proportional to the discharge. If discharge is decreased by, let us say 10%, area will also be decreased by 10%. If discharge is decreased by 20%, area will also be decreased by 20%, so that this velocity remains constant. Okay. Now have you understood how velocity is maintained constant inside this casing? Simply by reducing this area proportional to the consumption of discharge. Okay. Now if velocity is maintained constant, pressure will also be automatically constant. Why? See, this turbine will be installed in a horizontal plane. Excuse me. This turbine is installed in a horizontal plane. So there is no change in elevation. So if I draw one streamline like this, if I draw one streamline, so along this streamline there is no change in velocity because we are reducing area proportional to the consumption of discharge. So velocity remains constant. There is no change in elevation also because the flow is taking place in horizontal plane. So velocity constant, elevation constant. So pressure also has to be constant as per Bernoulli's equation. Okay, P by rho g plus V square by 2g plus Z is equal to constant. So this Bernoulli's equation should be satisfied inside this casing, right? Of course, here we are neglecting losses. So if you maintain constant velocity and constant elevation, definitely pressure has to be constant. Now if pressure and velocity, if both are constant, then flow conditions will be same everywhere. So in that case, each guide vane will take equal discharge. Agreed? So this is how spiral casing will distribute water equally to all guide vanes. Now after spiral casing, what is the next component? Next component is this guide vane. Guide vane is a stationary component. Okay, so this green color guide vane, it is a stationary. It is adjustable. Adjustable means we can tilt this guide vane about this hinge. So this is the mechanism which actuates the guide vane. So these guide vanes can be tilted around this axis, okay, by this mechanism. So you can see here, these are the top view of guide vanes. So these guide vanes can be tilted. So one position is shown here by solid black color, another position is shown by here dashed line. Okay, so after tilting, this flow area between the guide vanes can be adjusted. Now what is function of this guide vane, we'll discuss. So second component is guide vanes. So these guide vanes perform basically three functions. So first function, they guide water. Okay. Now what is meaning of guiding water? When water leaves this guide vane, it should enter tangentially to the runner. Entry should be smooth. Water which is entering into this runner, it should enter tangentially to this runner blade. If it is not entering tangentially, then entry will not be smooth. There will be entry shock, due to which there can be vibration also. And due to this entry shock, there can be flow separation also, and flow separation leads to loss. So what I am saying is, suppose this is a turbine blade, okay. So top view of turbine blade I am showing here. So when water enters into this turbine blade, the relative velocity of water, it should be tangential to the runner blade. VR1, 1 means inlet. So this is turbine inlet. So water is entering into the turbine from outer radius, right? So this water should enter tangentially. That otherwise entry will not be smooth, there can be entry shock. If this water direction, relative velocity direction, if it is not tangential, let us say direction is something like this, it is not tangential. So in that case, there will be flow separation on this side, and due to flow separation, eddies will be formed, and in fluid mechanics, you might have studied that due to these eddies, there will be loss also. So in that case, turbine efficiency will also come down. So due to entry shock, there can be vibration also, and due to these eddies, there can be reduction in efficiency of turbine also. That's why guiding of this water towards runner at proper angle is desirable, and that is the main function of this guide vanes. Okay. So this is first function. Second function, they act like nozzle. They act like nozzle. So what is function of nozzle? Function of nozzle is to convert pressure into kinetic energy. Now if you observe the flow area between these guide vanes, this flow area is decreasing. Flow area is decreasing. So when area decreases, naturally velocity has to increase and pressure has to decrease as per Bernoulli's equation. So these guide vanes perform similar function as that of nozzle in Pelton turbine. We have seen in Pelton turbine nozzle, pressure was converted into velocity. But there is one major difference between nozzle of Pelton turbine and these guide vanes. These guide vanes will not convert pressure completely into kinetic energy. Okay. So they convert pressure partially into kinetic energy. Partially into kinetic energy. Partially word is important here. Pressure is not completely converted into kinetic energy, unlike Pelton turbine. In Pelton turbine, nozzle completely converts pressure into kinetic energy. At the exit of nozzle, pressure is atmospheric pressure, which we consider 0. But here, if you see, at this point, at the exit of guide vanes, here if I take point, okay, so here this pressure is more than atmospheric pressure. So a few points I'll take here. So here pressure, let us say P1, it is more than atmospheric pressure. Okay, so point is exit of penstock. Here pressure is more than atmospheric pressure. At the exit of guide vane, let us say P2. This P2 will be less than P1. Why less than P1? Because some pressure is dropped inside this guide vane. When water is flowing through the casing, there is no change in pressure. Across guide vane, some pressure is dropped because this guide vanes will act like a nozzle. Velocity will increase, pressure will decrease. So this P2 will be less than P1, but still it will be greater than atmospheric pressure only. So what I am saying is all pressure is not dropped across guide vane. So remaining pressure will be dropped across this runner. When there is no drop tube, here pressure has to be atmospheric pressure. At the exit of runner, when there is no drop tube, pressure has to be atmospheric pressure. But when drop tube is used, so pressure at the exit will be less than atmospheric pressure. Okay. Now how pressure is varying? Understand carefully. At the inlet of turbine, pressure is highest. At the inlet of turbine or at the exit of penstock, pressure is highest. Inside casing, pressure remains same. Inside guide vane, there is a slight decrease in pressure, not complete. A part of pressure is dropped across guide vane. Remaining pressure is dropped across runner. Now this is fundamental difference between impulse turbine and reaction turbines. In impulse turbine, there is no change in pressure inside runner. If you remember Pelton turbine is exposed to atmospheric pressure. So there is no change in pressure inside Pelton turbine. But in reaction turbine runner, there is always a drop in pressure. That's why it is called reaction turbine. At the exit of turbine, pressure will be lowest. If drop tube is present, pressure will be less than atmospheric pressure at the exit of turbine. Have you understood how pressure is changing inside turbine? So second function of this guide vane is to convert pressure into kinetic energy, but not completely. Only part of pressure is converted into kinetic energy. Okay. Third function. Third function. They control discharge. They control discharge through the runner. Now how much quantity of water is passing through this runner, that is controlled by guide vanes. And how they control? By tilting. This mechanism will tilt these guide vanes across this vertical axis. If we tilt these guide vanes, flow area will modify. If flow area decreases, naturally discharge has to decrease. You can even completely close this guide vanes. Look at this position. Here guide vanes are completely closed. Now water cannot enter here. In that case, turbine will be stopped. So guide vanes can control discharge passing through this turbine by controlling this flow area. Now why we need to control discharge through the turbine? Just to control power output of turbine. Okay. If we send less discharge to the turbine, power generated by the turbine will be less. If you send more discharge, power generated by the turbine will be more, and so on. So these are the three functions of guide vanes. Now next component of turbine is runner. So this runner is main component of turbine. What is basic function of runner? To generate torque. To generate torque. Now why it is called runner? It is called runner because it is a rotating component. It is not a stationary component. Guide vane was a static component. Yes, they can be adjusted, but they are not rotating. They can only be tilted about axis. But this runner is a rotating component, and its function is to generate torque. Okay. Now how torque is generated? As I mentioned earlier, working principle for all turbines is same. To generate force or torque, you must change momentum of the fluid. Now how momentum is changed? That varies from turbine to turbine. Now look at this diagram. In Francis turbine runner, water enters radially inward and it leaves axially. So shape of the blade of modern Francis runner is three-dimensional. Okay, because water has to enter radially inward and then it is leaving axially. So shape of the blade is three-dimensional. But in analysis, while doing analysis, we assume that blade shape is only two-dimensional, like shown in this diagram. Okay, analysis for three-dimensional shape of a Francis turbine is nowhere given in any book, and that is beyond scope of your syllabus. Even when we study hydraulic turbines in separate subject as hydraulic machines, in that case also we do not perform dimensional analysis of Francis turbine blade. What we assume? Flow is entering radially inward and then it is leaving radially outward, like this. This kind of blade passage we are assuming. Flow is entering in radial direction and it is leaving in radial. So this design was classic Francis turbine design. So when Francis turbine was developed initially, it was having radial entry and radial exit. But modern Francis turbine is having radial entry and axial exit, something like this. Entry is radial but exit is axial. Shape of blade is three-dimensional. But for analysis, we are assuming only two-dimensional shape like this. Entry is radial and exit is also radial. That is for analysis. And this is enough for solving any numericals. So you won't get in exam numericals for three-dimensional shape of Francis turbine. Okay. Let's come to this main function, how torque is generated. As I mentioned earlier, to generate force or torque, you must change momentum of the fluid. Now look at this passage. When water is passing through this passage, flow area is decreasing. Outer radius is more, inner radius is less, so flow area is decreasing. So when flow area decreases, relative velocity will increase. Okay, so the passage will act like a nozzle. Relative velocity will increase. Again, here as blades are curved, direction of velocity is also changing. So in reaction turbine, magnitude of velocity is also changing and direction of velocity is also changing. So due to this change in magnitude of relative velocity and change in direction of velocity, there is a change in momentum of water, and angular momentum lost by the water per unit time, that is equal to torque. Rate of change of linear momentum is force and rate of change of angular momentum is torque. Here water is losing angular momentum and corresponding torque is generated by this runner. If you imagine that instead of this blade, you are putting your hand here, you will feel that force exerted by this water. When water is passed around your hand, water will try to push your hand in this direction. That's why this turbine blade rotates in this direction. Understood? So this is the working principle of Francis turbine. Now as I mentioned earlier, in reaction turbines, pressure will be dropped across runner also. Now, how pressure is dropped, that we are going to see here. In Francis turbine, pressure decreases due to effects. Pressure is dropped across runner due to two effects. So first effect is nozzle effect. Now what is meaning of this nozzle effect? Nozzle effect means the runner passage, it will act like a nozzle. Naturally here area is decreasing. So when area decreases, velocity has to increase, and when velocity decreases, when area decreases, velocity increases, and when velocity increases, pressure has to decrease. Understood? Same as in nozzle. In nozzle also area decreases, due to which velocity will increase as per continuity equation, and as per Bernoulli's equation pressure has to decrease. That is called nozzle effect. So due to this effect, from inlet to exit pressure will drop. This is one effect. Second effect is centrifugal effect. Okay. Now what is meaning of this centrifugal effect? If I take fluid particle inside this runner somewhere here, let us say I am taking here small fluid particle, same particle I am showing here. Okay. So this fluid particle, while flowing towards inlet, simultaneously it is rotating also, right? When runner blades are rotating, the fluid inside this passage, it is also rotating. So while passing towards exit, the simultaneously fluid particles are rotating, and we know that in rotational motion there are centrifugal forces. So this fluid particle experiences centrifugal force in radially outward direction. Let us say here somewhere center. So in radially outward direction there is a centrifugal force. So center I am showing here. Let us say center is here. So centrifugal force this particle will experience in radially outward direction. Value of the centrifugal force will be mass. Let us say mass of the small particle is dm into this radius r into omega square. This is the centrifugal force. Now there must be some another force which is balancing this centrifugal force, and that force is provided by pressure difference. So here there will be some pressure, let us say P1, and here there is some pressure, let us say P2. Okay. So pressure force is normal to the surface. On inner side of this element there is one pressure force, on another side there is another pressure. Now if you look at these forces, P1 is acting in radially outward direction, centrifugal force is acting in radially outward direction, and P2 is acting in inward direction. So force due to this pressure P2 is balancing force due to P1 and this centrifugal force. It means this P2 must be greater than P1. Are you getting this point? P1 is acting in inward direction. Sorry, P2 is acting in inward direction. P1 and centrifugal force, they are acting in outward direction. So this force due to P2 is balancing two forces. That's why P2 must have higher magnitude. So we can say that to overcome their centrifugal forces, pressure must decrease in radially inward direction. So this is called centrifugal effect. That's why due to these two effects, when water passes from inlet to exit, there is a decrease in pressure. Clear? And if you don't maintain pressure difference across this runner, this flow is not possible. To have this flow, there must be pressure difference across this runner. That's why entire pressure is not dropped across guide vane. We have discussed earlier, across guide vane only a part of pressure is dropped, remaining pressure is dropped across runner. Some pressure difference we must maintain across this runner, otherwise flow inside this runner is not possible. So after the runner, water will enter into this draft tube. Okay. A part of kinetic energy which is leaving this runner is extracted by draft tube. How draft tube performs this function? that we'll discuss separately. Okay students, now let us discuss how to draw velocity triangle for a Francis turbine. We have already discussed how to draw velocity triangle for a Pelton turbine. Am I right? The procedure to draw velocity triangle is exactly same. There are three main velocities, V, U and VR. Okay, V is absolute velocity of water, VR is relative velocity of water, and U is blade velocity. Am I right? I hope you remember these notations. We have already used these notations, and we have discussed also absolute velocity of water is equal to velocity of blade plus relative velocity of water with respect to blade. Okay, so even though this water is stationary inside this runner, it will have velocity equal to blade velocity. If it is moving, then additionally it will have relative velocity. That's why this relation is coming. So whenever you want to draw velocity triangle, the first velocity vector you should draw is, yes, relative velocity. Why? Because direction of relative velocity is known. The relative velocity at inlet, it must be tangential to this blade profile. Okay, so this is Francis turbine blade. So this is outer periphery of Francis turbine runner, this is inner periphery. Always whenever you want to draw velocity triangle, first you show this outer periphery and inner periphery so that you can get better judgment of different directions. So this relative velocity should be tangential to the blade profile. The reason is the relative velocity should be such that, because in this situation only entry shock or separation loss will be minimum. At inlet, that's why this is VR1. Similarly, exit relative velocity, it will also be tangential to the blade profile. So at exit, that's why this is VR2. Why exit velocity has to be tangential? Because when flow is passing through this runner passage, flow has no other way to go, it has to follow this curvature. So at exit, flow is forced to follow the curvature, that's why it is tangential. There is nothing like exit shock, please remember. Then in relative velocity, if you add blade velocity, you will get absolute velocity. But as we discussed earlier, whenever you want to do addition of these vectors, you have to follow triangle law, because these vectors are having different directions. Now think for a while and tell me, what should be the direction of this blade velocity? Blade velocity at inlet. You can pause video and you can think. Okay. This blade is performing circular motion. In circular motion, velocity is tangential to the circle. Am I right? Velocity is tangential to the circle. That's why blade velocity vector you should draw in tangential direction, parallel to tangent at this point. Okay. And you should add this vector such that triangle law is followed. This is blade velocity at inlet, that's why U1. See, am I following triangle law? Whenever first vector is ending, second vector is starting. You can add this blade velocity vector. Instead of before relative velocity, you can add here after relative velocity also. That is also okay. Then by triangle law of vector addition, resultant vector will start at starting point of first vector and it will end at end point of second vector. Please remember these directions. Relative velocity is tangential to the blade profile and blade velocity is tangential to the periphery. That's why it is important to draw these peripheries. And once you know these two directions, you can draw direction of absolute velocity. So this is absolute velocity at inlet, that's why this vector should be V1. The same principle will follow at exit velocity triangle also. After relative velocity, we should add blade velocity. Okay. At this point, blade velocity will be tangential to the circle. So in tangential direction, I am adding this vector. This is U2. And once again confirm whether you are following triangle law or not. Whenever first vector is ending, second vector is starting. So resultant vector will start at starting point of first vector and it will end at end point of second vector. And this is V1. Okay. And in Francis turbine, the profile of blade is designed in such a way that Under normal operating condition, under design conditions, the exit velocity triangle will be right angle triangle. This angle is 90 degree. Understood? So this is how we have to draw velocity triangles. Apart from these triangles, in triangle there are three main velocities. Apart from these three velocities, there are two additional velocities. One is called velocity of whirl, velocity of whirl, and another is called velocity of flow, velocity of flow. Okay, but please remember, these are not additional or new velocity vectors. These are just components. These are components of this absolute velocity. Okay, these are not new vector, these are components of absolute velocity. Okay, the velocity of whirl is defined as component of vector absolute velocity vector v along blade velocity, and velocity of flow is normal component. So this is component of vector v perpendicular to blade velocity. These are the definitions. I will show those components in this diagram. This is absolute velocity, component of absolute velocity along blade velocity. So draw lines perpendicular to u. So this distance indicates velocity of whirl at inlet, that's why 1. So this is absolute velocity, its component along blade velocity, that is Vw1, and other or normal component, this is called velocity of flow at inlet, that's why 1. Okay, at exit, absolute velocity is perpendicular to the blade velocity. So component along blade velocity will be 0. Am I right? Component along blade velocity will be v1 cos 90. So it will be 0. Component along blade velocity is whirl velocity. So at exit, Vw2 is equal to 0. That's why v1, this is v2. This is not v1. v2 and vf2 will be same. Okay. So these are the whirl and flow component. In addition to that, there are two angles also, alpha and beta. Okay, let us see how these angles are defined. Alpha is called guide vane or blade angle, guide blade angle. Guide vane and guide blade meaning same. And beta is called runner blade angle, runner blade or vane, same. Meaning of word blade and vane is same. Okay. So how these angles are defined? This guide vane angle is angle between, this is angle between absolute velocity vector and blade velocity. Runner blade angle, this is also angle between relative velocity and blade velocity. Okay. So if you observe this definition, whirl component, flow component, alpha, beta, everywhere reference is this blade velocity. Remember this point. For resolution of these components as well as for measurement of angle, reference is blade velocity. Okay. Angle between absolute velocity and blade velocity is guide vane angle. So look at this velocity triangle. This is absolute velocity and this one is blade velocity. So in between this angle is alpha. Come right here, alpha at inlet, that's why 1. Okay. Angle between blade velocity and relative velocity. Okay. Now here there are two angles, one is exterior, one is interior. So many people get confused. So I'll tell you simple trick to remember. See, different authors have given different definitions of angle, but always angle will be between these velocities only. But some authors will take on outer side, some author will take on inner side. I'll tell you simple trick to remember. Whenever you are showing any angles for hydraulic machines, show angles on interior side. Okay, so this is beta 1. Always show angles on interior side. So this is alpha 2, 90 degree, and this one is angle between relative and blade, so it is beta 2. So for hydraulic machines, you can use this notation, show all angles on interior side of triangle. If you are mechanical students and if you are studying steam turbines and gas turbine, their notations may be different, but there also alpha will be always between absolute velocity and blade velocity, beta will be always between relative velocity and blade velocity, but notations will be slightly different. Hello friends, today we are going to discuss very important concepts of Euler turbine equation. As you may be knowing, all hydraulic machines work on this equation, and Euler's turbine equation, it is derived based upon principle of angular momentum. So as per principle of angular momentum, torque generated by runner, it must be equal to angular momentum lost by water, must be equal to angular momentum lost by water. So this is working principle for all turbines. As I mentioned earlier, all turbines work on this principle. In order to generate torque, you must change momentum of a fluid. When water is flowing through this runner, its direction will change continuously. Due to change in direction, there is change in momentum, and angular momentum lost by water is equal to torque. This is working principle for all turbine, let it be hydraulic turbine or steam turbine or gas turbine. For all turbines, this is the working principle. Okay. Now T, mathematically we can write this as torque T is equal to angular momentum lost by water, means initial angular momentum minus final angular momentum. Angular momentum is moment of linear momentum. Okay. So linear momentum formula is m into v bar. Angular momentum means its moment. So take moment of this linear momentum vector about center. So to take moment, we will take cross product with position vector. So this is position vector at inlet, R1 indicates position vector at inlet, so R1 into mv bar. So this is angular momentum at inlet. Okay. So angular momentum lost by water, it should be per unit time. Then we will get rate of change of momentum, am I right? Rate of change of momentum is equal to torque. So angular momentum lost by water per unit time. So that's why here instead of mass, you should take mass flow rate. Same quantity we would calculate at outlet. R bar cross. This cross products for moment. M dot into vector V at exit. So difference between these two is nothing but torque. Okay. Now before proceeding further, let us revise velocity triangle for a Francis turbine. Whenever you want to draw velocity triangle for any turbine or pump, you should always show relative velocity, because its direction is along the blade profile at inlet as well as exit. At inlet, it will be along to avoid entry shock, and at exit it will be by default, it will be along because flow has no other way to go. Then in relative velocity, we should add blade velocity. Remember this identity. Absolute velocity vector is equal to blade velocity plus relative velocity. So this addition you should always do by following triangle law vector addition. Okay. Then you will get absolute velocity. One more thing which I forgot to mention earlier, relative velocity is along blade, but what is the direction of this absolute velocity? Okay. Let us understand the difference between relative and absolute first. If you stand on this turbine blade and if you observe the flow, you should see relative velocity, and when you stand on ground and if you see flow, you should see absolute velocity. If you remember, before this runner, guide vanes are present. Am I right? Before the runner, guide vanes are present, and guide vanes are stationary component. When you stand on the guide vane, you should see absolute velocity of water. Okay, so that's why this absolute velocity would be along guide vane. Before this, there is stationary component called guide vane. So along guide vane, this absolute velocity should be there. That's why angle made by absolute velocity, this alpha, it is called guide vane angle. All these names are logical: blade angle, guide vane angle. Relative velocity is along blade. That's why angle made by relative velocity is called blade angle, and angle made by absolute velocity is called guide vane angle, because this absolute velocity vector, it is along guide vane. Why along guide vane? Because guide vane is a stationary component, and velocity with respect to stationary component is absolute velocity. Please remember these things. Next, now I want to take this cross product. Okay, see, this is absolute velocity vector, same vector I have shown here. Component of absolute velocity along blade velocity, this is velocity of whirl. Okay, so this is velocity of whirl, so this is also velocity of whirl, and the normal component, this is velocity of flow. So these two components I have shown here. Now to take moment, there are two ways. Either you take moment of entire vector, resultant vector, or you can take individual moments of this component. First you take moment of Vw1, then you take moment of Vf1, and then you add. Both cases will give same result. This is called Varignon's principle. You might have studied this in mechanics. It says that moment of a vector equal to sum of moments of its components. So Vw1 and Vf1 components of V1. So that's why sum of their moments must be equal to moment of V1. Okay. Another thing, important thing to note here is, why to take moment of absolute velocity vector only? Why not relative velocity? This relative velocity vector also you can take, right? Please remember, this is Newton's second law. This equation you are getting Newton's second law, and all Newton's laws are valid in inertial frame of reference. So this term you might have studied in mechanics. Frame of reference should be inertial. Okay, the meaning of this inertial frame is acceleration of inertial frame is 0. So either stationary frame or frame which is going with constant velocity, those are inertial frame. So in inertial frame only you have to apply this law. Okay, if you take runner as a frame, then you will see this relative velocity, this one. Vr1 is velocity of water in the frame of runner, and runner is not inertial frame because runner will have acceleration, because runner is performing circular motion. Am I right? Runner is performing circular motion about center, and in circular motion inherently always acceleration is present, v square by r. Okay, even though it is rotating with constant angular velocity, still acceleration will be present, and its value is v square by r or omega square. That's why Newton's law is not valid in the runner frame. You should apply Newton's law in the inertial frame, and ground frame is inertial frame. That's why this vector we should take as absolute velocity, not relative velocity. Understood? Now let us take moment. Now what we'll do, we'll resolve this vector into two components, Vw1 and Vf1. If you observe here, velocity of flow is along radius. Okay, it is perpendicular to the tangent, means it is along radius. That's why it will pass through center, so it will not make any moment. Velocity of whirl, it is tangential. As it is tangential, it will be perpendicular to the radius. This angle will be 90 degree. So its moment will be say r1 into m dot Vw1. That's it. Similarly, r2 into m dot Vw2. M dot is scalar and this constant we can take it out. So m dot I can write rho into q, volumetric flow rate into density, that is mass flow rate, into r1 Vw1 minus r2 Vw2. Okay, this is called Euler equation of turbo machines. Euler turbine equation. This is valid for all turbines, steam turbine, gas turbine, hydraulic turbines, all turbine work on principle of angular momentum, and this is valid for all turbines. For pump also you will get similar equation, but it will be reverse, because turbine is torque generating device, pump is torque consuming device. So that's why this terms will be reversed. That is the only difference. Okay. So for pump equation, I will not derive the formula again. For pump, you will get similar equation. I'll just write directly rho Q R2 VW2 minus R1 VW1. So this is Euler's pump equation. Okay, because pump runner will be exerting torque on a liquid, am I right? That's why momentum of liquid will increase. That's why final minus initial. And turbine is torque generating device, so momentum of water will be lost. That's why initial minus final you have to take. So this is the only difference. Okay. In case of Francis turbine, if you observe carefully, in case of Francis turbine, VW2 will be 0. That's why second term we need not to consider. And why I am showing this as a vector? Because sometimes it is possible that VW1 is forward and VW2 is backward. In that case, the moment sign will be opposite. So minus minus you have to take here plus. Okay, that's why this vector notations I am giving. In case of Francis turbine, VW2 is 0. Okay, so no need to write these vectors because only first term will be present. So for Francis turbine, we can say this is 0. VW2 is 0. Okay, please remember this. I hope you understand Euler turbine equation. Hello students, now let us discuss how to find out discharge for a Francis turbine. Okay. First things which comes into mind is discharge is equal to area into velocity, am I right? This equation we use very commonly in fluid mechanics, discharge equal to area into velocity. Okay. But normally many students will not be knowing that if velocity is not perpendicular to the area, then which velocity we should consider, am I right? Let us say this is flat surface and velocity vector, it is not perpendicular, it is making some angle. In such case, if you calculate discharge is equal to area into actual velocity or absolute velocity, you will not get correct answer. Okay. In such cases, we have to resolve this vector into two components. Velocity vector you resolve into two components, normal and tangential. Okay. To calculate discharge passing through this area, you should always consider normal component. Why normal only? Because this component only is responsible for discharge which is crossing the area. Let us imagine at this point here there is only tangential component, there is no normal component. So due to this tangential component, what will happen to the flow? Flow will go along the area, it will not cross the area, am I right? This fluid particle will move in this direction. So tangential component is not responsible for discharge which crosses the area. That's why to calculate discharge which is crossing the area, we should consider normal component. Please remember this point, Q is equal to area into normal velocity. This is general relation. Many people will be knowing Q is equal to area into velocity, but whenever area and velocity are not perpendicular, you should take normal component. In most situations, like in pipe flow, velocity will be normal to the area. So this pipe flow, cross sectional area of pipe is like this, and velocity vector will be normal. So that's why we don't worry much. But whenever velocity vector is not normal to the area, we should consider normal component. Now observe this flow. This is Francis turbine runner. As you may be knowing, Francis turbine is radially inward flow, so discharge will go in this direction. Okay, so it will enter at outer radius, then it will flow through this passage, and through the inner radius it will exit. Same top view of the same flow is shown here. So flow will be going in this direction and through here it will go out. In reality, flow will be slightly in 3 dimensions. This blade will be complex, but for analysis we will consider only 2-dimensional turbine. The original Francis turbine runner which was developed, it was 2-dimensional only, radial in, radial out. Nowadays modern Francis turbine is radially inward only, but discharge is radially inward at inlet, and exit it will be axial, it will be going in this direction like this, okay. But in that case we are not going to do any analysis. Our analysis is valid for original Francis turbine design. Whatever question which come in exam, those questions are for original Francis turbine only. For modern Francis turbine there is no analysis. Fine. So discharge, here it is passing through area. If you imagine the shape, the shape is inlet shape. This is inlet area. So it is a cylindrical area, am I right? It is not a circular area. Discharge is not going in this direction. It is a cylindrical area. Discharge is going through the circumference. Let us imagine. So this is turbine runner. So discharge is going through this area, cylindrical area. The cylindrical area is pi d into width. So discharge is equal to flow area into velocity, normal component of velocity. Okay. Flow area is pi d. At inlet flow area is cylindrical, so pi d is width at inlet, that is why 1 into width of the runner at inlet is b1. So this is flow area. Okay. Now what is normal component of velocity? To the cylindrical area, this is absolute velocity vector. Absolute velocity vector is not normal. So at this point, if you draw the normal, here, normal should be along radial direction. So normal velocity is velocity of flow. So this normal component of velocity, it is nothing but velocity of flow at inlet. So that's why here you should take Vf1. Understood? Area is cylindrical area, that's why pi db, and normal velocity is velocity of flow. As discharge depends upon normal velocity, this normal velocity component is called velocity of flow. Those things are having some meaning. Velocity of flow is not called just like that velocity of flow. Discharge or flow depends upon velocity of flow, that's why it is called velocity of flow. Similarly, if you remember the Euler turbine equation is equal to torque is equal to rho q Vw1 into R1. This is for Francis turbine. Am I right? For Francis turbine Vw2 is 0. As torque depends upon tangential component, the tangential component is called velocity of whirl. Whirl means rotation. Tangential component is responsible for rotation of turbine. That's why it is called velocity of whirl. So these names are logical. Similarly, now if you want to find out discharge at exit, Q exit, if you want to find out, you should take area of flow at exit into normal velocity at exit. So this is normal velocity at inlet. Area of flow at exit is equal to pi d to b2. Exit area, this one is the exit. Exit is also cylindrical. So exit width and inlet width may not be same. So pi d to b2 in Vn2 is Vf2. Okay. So this is flow area. And this one is normal velocity. Let us discuss now power developed by Francis turbine runner. In short, it is called RP. RP means runner power or rotor power. Please remember this notation. In case of Pelton turbine also, we have used same notation. RP means runner power. Okay. To calculate runner power, we should first calculate torque. Okay. Torque T, it is given by Euler's turbine equation. Am I right? Torque is equal to rho q R1 Vw1 vector minus R2 VW2 vector. This is called Euler's turbine equation. This we have derived earlier. Okay, where VW1 and VW2 are velocities of whirl or tangential component of absolute velocity. If you remember, for Francis turbine, exit velocity triangle is right angle triangle. That's why VW2 is 0. Okay, therefore equation of torque for Francis turbine is rho q VW1 into R1. Now, no need to write this vector sign. This vector sign we write only when VW1 and VW2 both are present. So they may be in same direction or they may be in opposite direction. So to take care of that, this vector sign is used. But if only one component is present, no need to write vector. So rho q VW1 into R1. So this is equation of torque for Francis turbine. This is for Francis turbine. Okay. So power we'll calculate now. Power or runner power is equal to torque into angular velocity. The torque formula is rho q VW1 into R1 into angular velocity. What is this R1 into angular velocity? Radius into angular velocity will give tangential velocity. Am I right? Tangential velocity of runner. So this is U1. So runner power becomes rho q VW1 into U1. This is expression for runner power. Okay. No need to remember this expression separately. What you should remember is only Euler turbine equation, and for Francis turbine VW2 is 0. So if you take VW2 0, you will get torque equation for Francis turbine. Power is equal to torque into angular velocity. That's it. You can derive this equation very quickly. Hello students. Now we'll discuss various losses in Francis turbine. Okay. Let us consider this is Francis turbine installation. From here, water will be coming from penstock. Okay. So penstock exit, it is considered as an inlet to the turbine system. Through the penstock, then water will be going into the turbine. Inside turbine, first there will be spiral casing. After spiral casing, there will be guide vanes. After guide vanes, there will be runner. After runner, then water will be going through the draft tube, and through draft tube it will go into the tail race. So this is flow passage. Okay, we have discussed this thing earlier also. Whenever we started with Francis turbine, basic components we have studied. I hope you remember. So water will be coming from penstock. After penstock, scroll casing. After casing, guide vanes. After guide vanes, runner, and after runner, water will go into draft tube. Okay. When water is flowing through all those components, there will be always loss due to fluid friction. Okay. In addition to that, if entry is with shock, ideally entry should be without shock inside runner, but sometimes there can be entry with shock, especially when turbine is operating under park load condition. Okay. So in such cases, there will be shock loss also. All those losses are related to the water, and those are called hydraulic losses. Okay. Hydraulic losses means losses which are related to water. If you subtract hydraulic losses from the inlet energy, okay, inlet energy is represented by net head. Net head is energy difference between inlet and exit of turbine, exit of draft tube. I hope you remember definition of net head. Net head is energy head difference between inlet of turbine and exit of draft tube. This is energy lost by the water. So all that energy is not going to convert it into useful mechanical work. Okay. So part of that energy is lost due to hydraulic friction. Energy represented by net head is called hydraulic power. So let us say this first column represents hydraulic power. Okay. So this is highest possible energy in the turbine system. It represents energy which is lost by water. So out of that energy, some part will be lost due to various hydraulic losses. Hydraulic losses means losses which are related to water, fluid frictional loss and shock loss. You can write here friction plus shock loss. This is not mechanical friction, fluid friction. Fluid friction plus shock, those are hydraulic losses. Okay. If you subtract hydraulic losses from the energy lost by water, then you will get mechanical power developed by the turbine, but entire that power is again not useful. If you subtract this, you will get runner power. Runner power means theoretical power developed by the turbine, but all theoretical power is not transferred to the generator, because this turbine and generator are connected together by shaft. Sometimes there can be gearbox also, shaft, gearbox, and in all those mechanisms there will be friction, mechanical friction will be there. Inside gears also there will be mechanical friction. So if you subtract those mechanical losses, final power is transferred to the generator, that is called shaft power. Shaft power means power which is transferred to the generator. So difference between runner power and shaft power is mechanical losses. Okay. Mechanical losses such as bearing friction. And final will be the shaft power. So in between these two powers, first two powers, the efficiency which is defined is called hydraulic efficiency. Why name hydraulic efficiency? Because hydraulic efficiency considers hydraulic losses. Between runner power and power, efficiency defined as mechanical efficiency, because it considers mechanical losses. These things we have discussed earlier also. Between initial input and final input, efficiency which is defined is overall efficiency. Okay. Again I am repeating, hydraulic power means power of a water. It is represented by net head. Net head means energy head lost by water. It is energy head difference between inlet of turbine or exit of penstock and draft tube exit. Okay, that is net head. Out of net head there will be fluid frictional loss. If you subtract that, you will get runner power. From fluid frictional loss, from runner power, if you subtract mechanical frictional loss, you will get shaft power. Okay. Now let us discuss formulas for each efficiency. First is hydraulic efficiency. So here I am writing hydraulic efficiency. Hydraulic efficiency, it is denoted by eta suffix h, and its definition is runner power divided by hydraulic power. So formula for runner power is rho q Vw1 u1 and hydraulic power is rho g qh. So hydraulic efficiency you will get rho q cancelled, Vw1 u1 divided by g into h. And this is formula for hydraulic efficiency. Okay. Then we will see mechanical efficiency. Mechanical efficiency formula, mechanical efficiency, it is denoted by eta m. Mechanical efficiency formula is shaft power divided by runner power. And overall efficiency, it is denoted by eta suffix o, and its formula should be Sp divided by Hp. So you can rearrange this also. This is equal to Rp divided by Hp into Sp divided by Rp. So Rp you can cancel. So this is also equal to Rp divided by Hp is hydraulic efficiency and Sp divided by Rp is mechanical efficiency. So overall efficiency is product of these two efficiencies. So once you understand this energy diagram, so from this energy diagram you can easily get formulas for various efficiencies. Similar thing we have discussed in Pelton turbine also. Okay, in Pelton turbine there was additional efficiency called nozzle efficiency. Now here there is no nozzle, so that's why nozzle efficiency we are not writing. Hello students, today we will discuss concept of speed ratio and flow ratio in case of Francis turbine. In similarity laws, we will show that any velocity is directly proportional to root h. Okay, the similarity laws are used to compare results of different types of turbine. Means turbine should have same geometric shape, but sizes can be different. In this case, you can use the similarity laws. We'll see those similarity laws in details later. It means any velocity like velocity of flow, blade velocity, absolute velocity, relative velocity, any velocity, whether at inlet or exit, any velocity is directly proportional to root h. So from here I can say that u is directly proportional to root h, or u by root h is equal to constant. Okay, so these similarity laws are valid under two conditions. So first condition is similar shape or similar geometry. Shape should be same. Second condition is similar velocity triangles. Similar velocity triangles. Under these conditions, these similarity laws are valid. Okay. Now, for Francis turbine, speed ratio is defined as Ku is equal to U divided by root h. Okay. When turbine is at optimum condition, shape of velocity triangle will be same. Okay, we'll discuss this thing in the similarity analysis. When turbines are running under optimum condition, shape of velocity triangle will be same. So in such cases, this ratio u by root h ratio, it is only function of geometric shape. So speed ratio is function of geometric shape alone. Okay, so sometimes instead of specifying speed ratio is specified because this is constant for a given geometric shape of a Francis turbine. For Francis turbine, this range is around 0.72 to 0.82. No need to remember this number. These things will be given in the exam. I am just giving this for information. You might be remembering, in case of Pelton turbine, we have discussed or we have defined speed ratio as Ku is equal to U divided by root 2 gh, where U is bucket speed and root 2 gh is theoretical jet speed, and this is approximately equal to U by V. Why approximately? Because in case of Pelton turbine, V is equal to actual jet velocity is equal to CV times root 2 gh. So there is a factor of CV between root 2 gh and V. That's why there will be small difference, but these two values will be close enough. So some author define speed ratio for Pelton turbine as U by V also. That is okay. But please remember, important point here is this definition is not valid for Francis turbine. For Francis turbine, speed ratio is always defined like this. This definition is not valid. Why not valid? In case of Pelton turbine, entire pressure is converted into velocity inside nozzle. But in case of reaction turbine, only a part of pressure is converted into kinetic energy inside guide vanes and remaining part is dropped inside runner. So this V or V1 in case of Francis turbine is not even nearly equal to root 2 gh. Okay, so these two values will be quite different. So for Francis and Kaplan turbine, speed ratio is defined like this, not U by V1. Please remember this. Okay. Another thing is for Francis turbine, U1 that is blade velocity at inlet and blade velocity at exit may not be same, because inlet radius and exit radius are different. So u is equal to r into omega, so these are different. But in case of Pelton turbine, as cross section of a bucket, it is taken at particular radius. So u1 is equal to u2 here, and this is equal to pi dn divided by 60. But for Francis turbine, d1 d2 are different, so u1 u2 will be different. So that's why this speed ratio, it is defined based upon blade speed at inlet. Okay, and there is no proof for this. These are the definition. Please remember, these are the definition. There is no proof for this. So speed ratio is defined in this manner only, but this ratio will be constant for a given geometric shape. So instead of specifying bucket speed, blade speed, the speed ratio is defined because it is a constant for a given geometric shape. u1 may vary based upon size as well as based upon operating condition, but ku will be same. So this is pure function of geometric shape. Similarly, as any velocity is directly proportional to root h, velocity of flow will also be directly proportional to root h. So this kf, which is defined as vf divided by root 2gh, this is also constant. So this is also function of geometric shape. Okay, and for Francis turbine, this value varies between 0.15 to 0.3. Again, no need to remember this number. These numbers will be specified. Okay, so what you should remember is the definitions. Speed ratio is defined as u divided by root 2gh, and blade velocity is taken at inlet. Similarly, here also flow velocity is taken at inlet. This thing you should remember. This is simple theory question which is asked based upon general knowledge. Which one of the following statements is true? Both Pelton and Francis turbine are impulse turbine. No, Francis is not impulse turbine, it is a reaction turbine. So first statement is wrong. Francis turbine is a reaction turbine, but Kaplan turbine is impulse turbine. No, this statement is wrong. Second part of the statement is wrong. Kaplan turbine is also reaction turbine. So B is also wrong. See, Francis turbine is axial flow reaction turbine. Francis turbine is reaction turbine, but this axial flow is wrong. It is radially inward flow, or you can say mixed flow also. Okay, so this C is also wrong. So D has to be correct. Kaplan turbine is axial flow reaction turbine. That is correct. So answer is D. So such simple question is asked. This question most of the students will be able to answer based upon general knowledge. So mostly if you see the previous gate question, this kind of simple theory questions they are asking. I have given you one table. So based on that table, most of such questions you can answer. Look at this question. This question is related to Francis turbine. First read the question and try to understand the given data. So here I am listing the given data. A Francis turbine under a Francis turbine of 1.6 meter runner diameter. So this is runner diameter. Runner means outer diameter, but outer diameter is diameter at inlet. Am I right? In case of Francis turbine, flow enters from outer diameter to inner diameter, right? Flow enters in radially inward direction. So outer diameter is nothing, diameter at inlet. Inlet is indicated by 1, exit is indicated by 2. So this is D1. Have you understood this point? This is slightly confusing. Outer diameter is at inlet and inner diameter is at outlet. Okay, because flow is entering in radially inward direction. That's why. Works a net head of 80 meter. So H is given 80 at 300 rpm. So N is 300 rpm. If the guide vane angle is 10 degree, what is meaning of guide vane angle? Guide vane is present in inlet, right? And it is a stationary component. So angle made by guide vane is alpha. Alpha 1 is given 10 degree. This is most important point. The radial component of absolute velocity is 5 meter per second. So what is meaning of radial component of absolute velocity? Okay. So first we'll draw the triangle. If you are not able to understand this, what is this radial component? First you draw velocity triangle, then you'll come to know. So whenever we draw velocity triangles, always first we'll draw relative velocity. At inlet as well as at exit, relative velocity should be tangential, right? So this is VR2, this one is VR1. It should be tangential to the blade. Then in relative velocity, we will add blade velocity. Blade velocity is along tangent to the circle. So this is U1. Here also blade velocity will draw tangent to the circle, parallel to this line. So this is U2. Absolute velocity is vector sum of these two. Okay. So we should add this vector such that triangle law is followed. So whenever first vector is ending, vector is starting. Resultant vector will start from starting point of first vector and it will end at end point of second vector, V2. So here this is V2. Okay. And for Francis turbine, exit velocity triangle is right angle triangle. So this alpha 2 is equal to 90 degree, V2 will be equal to Vf2 and Vw2 will be equal to 0. So this angle between relative velocity and blade velocity, this is beta 2. This angle is alpha 1. This is beta 1. Okay. Now there are two more components. Component of absolute velocity along blade velocity. This is called velocity of whirl. Okay. So this Vw1, it is component of absolute velocity along blade velocity. The other component which is in perpendicular direction. Okay, so this component, this is velocity of flow. What he has given? Radial component of absolute velocity. Now absolute velocity is having two components. One component is tangential, another component is perpendicular. So direction perpendicular to the tangent is radial direction, correct? So radial component of absolute velocity means Vf1 is 1. Vf1 is 5 meter per second. Again I am repeating, absolute velocity is having two components. One is tangential to the circle, that is velocity of whirl. Another is perpendicular to this Vw1. Perpendicular to the tangent means this is radial. This component will pass through center of the runner. Okay. Hydraulic efficiency of the turbine correct to 1 decimal places. Now what is formula for hydraulic efficiency? Hydraulic efficiency is equal to Vw1 U1 divided by G into H. This is the formula for hydraulic efficiency. So here H is given, G we can take 9.81, U1 we can calculate using speed, right? Speed is given and diameter is given. From that U1 we can calculate. And this Vw1 we can calculate from this alpha. Okay. So from this triangle, tan of alpha 1 is equal to opposite side. Opposite side is Vf1. Adjacent side that is base of triangle is Vw1. So from here Vw1 is equal to Vf1 divided by tan of alpha 1, and U1 is equal to pi d1 into n divided by 60 divided by G into H. Now substitute these values. Hydraulic efficiency is equal to Vf is 5 divided by tan of 10 into pi, D is 1.6, N is 300 divided by 60, volt divided by G is 9.81 into H, 80 meter. Okay. So this first bracket, this is VW1. The second bracket is U1 divided by G into H. So if you do these calculations carefully, you should get efficiency around 90.8%. Hello students, please read this question. This is very good question which was asked in Mechanical Engineering 2007 GATE for 2 marks. In GATE, till now on Francis turbine from 2007 onwards, there is only one numerical, and on Kaplan turbine till now there is no numerical. So generally in GATE exam on turbines you won't get much numericals, but this numerical was asked and it is very good numerical. So most of the students make mistake while solving this numerical. You can pause this video and you can try to solve this question. Now I'll explain the solution. Now try to understand the given data, what is given in the question. Given data. The inlet angle of runner blades of Francis turbine is 90 degree. Inlet angle of runner blades. This is runner blade angle at inlet. So with our notation it is beta 1. So beta 1 is given 90 degree. Fine. The blades are so shaped that the tangential component of velocity at blade outlet is 0. Tangential component of blade velocity. It means it is velocity of whirl. Velocity of whirl at blade outlet, that is VW2 equal to 0. It is equal to 0. Okay. So this condition is not need to be mentioned specifically. Once they say Francis turbine, so by default for Francis turbine, VW2 is equal to 0 and alpha 2 equal to 90 degree. Exit velocity triangle for Francis turbine will be always 90 degree. This is how Francis turbine runner blade is designed. Okay. Anyway, they have mentioned this condition, so no issue. The flow velocity remains constant. The flow velocity remains constant throughout the blade passage, means at inlet and exit flow velocity is same. So Vf1 is equal to Vf2 and this is equal to and is equal to half of the blade velocity at runner inlet. Half of the blade velocity means U, at inlet means U1 divided by 2. So this condition is given. Okay. The blade efficiency of the runner is, so what we have to find? Blade efficiency. Now what is meaning of blade efficiency? This concept of blade efficiency we have not discussed. Blade efficiency means runner efficiency. Runner efficiency means hydraulic efficiency. Okay. So hydraulic efficiency basically he is asking. What is formula for hydraulic efficiency? Formula for hydraulic efficiency is equal to U1 VW1 divided by G into H. Now if you look at this question, numerical values for any of the parameter is not given. So we have to express this head in terms of velocities and see how it turns out. Okay. So for that purpose, first we will draw velocity triangle. This is the runner blade for Francis turbine. Now we have to draw velocity triangle. Now how to draw velocity triangle? First we should draw relative velocity. The relative velocity is tangential to the blade profile. Relative velocity is tangential to the blade profile. So this is relative velocity at inlet. So VR1. This one is relative velocity at exit. So VR2. Fine. Now listen here. In the question it is mentioned beta 1 is equal to 90 degree. Beta 1 is angle made by relative velocity with blade velocity. Blade velocity will be tangential to the circle. So along this tangent to the circle, we have to draw blade velocity, right? And angle between blade velocity and relative velocity is 90 degree. So this is beta 1. Beta 1 is angle between velocity and blade velocity, and it is given as 90 degree. It means our inlet velocity triangle will be right angle triangle, right? So this beta 1 equal to 90 degree. Absolute velocity is vector sum of blade velocity and relative velocity. So this is V1. Angle made by absolute velocity with blade velocity, this is alpha 1. Now we will do exit velocity triangle. In exit velocity triangle also, in relative velocity we have to add blade velocity, and blade velocity will be tangential to the periphery. So at this point, if you draw tangent to the runner circumference, along this we should draw blade velocity. Okay, so blade velocity vector I am drawing now parallel to the tangent. This is u2, and absolute velocity is vector sum of blade velocity and relative velocity. So this is v2. In Francis turbine, the exit velocity triangle will be by default right angle triangle. So this angle is 90 degree. So this is alpha 2. Alpha 2 is equal to 90 degree, or this VW2. VW2 means tangential component of absolute velocity. If you take component of absolute velocity along blade velocity, so that has to be 0. So this thing is mentioned in the question, even though it is not mentioned. So by default you have to take alpha 2 equal to 90 degree and VW2 equal to 0 for Francis turbine. Now this angle is beta 2, angle between relative velocity and blade velocity, beta 2. Okay, so these are the velocity triangles. Now if you look at this inlet velocity triangle, component of this absolute velocity along blade velocity, so this is called VW1. As this is a right angle triangle, component of absolute velocity V1 cos alpha will be equal to U1, right? And other component of absolute velocity normal to the blade velocity, that is VF1, and this VF1 must be equal to relative velocity. Now in the question this condition is given, VF1 is equal to VF2 and it is equal to U1 by 2, right? So VF1 I can write U1 by 2. So this is equal to U1 divided by 2. Here VW2 is equal to 0, so V2 will be equal to VF2 and VF2 is also equal to U1 by 2. So this condition is given in the question. So we have finished velocity triangles with relative values. Okay, so let us come to our question. So we got expression for hydraulic efficiency like U1 VW1 divided by G into H. Now U1 is equal to VW1, so I can write this as a U1 square by G into H. Numerical values for U1 and H, those are not given. Now somehow we have to relate this head with velocities. Now how to do that? This is the most critical step. You can pause the video and you can try to think how to relate U1 and H. Okay, now I'll tell the solution. Many students make mistake here. What they will think is input energy is kinetic energy here. So that's why input head they will take V1 square divided by 2G, assuming that input energy is kinetic energy. But this is wrong. You should not do this. Why? Because this Francis turbine is a reaction turbine. In reaction turbine, we have studied that in runner pressure decreases. Okay. In other words, there is a conversion of pressure into work inside runner. Or we can say at inlet of the runner, energy is available in the form of kinetic energy as well as pressure energy. So if you are equating this head equal to kinetic energy, that means you are ignoring pressure energy part. Okay, and this pressure energy part is significant. In case of impulse turbine, H and V1 square by 2G, those are nearly equal because pressure energy is 0. But in case of Francis turbine, there will be much difference between H and V1 square by 2G. Actually, this H is equal to V1 square by 2G plus pressure energy. So this pressure energy part we are completely ignoring if we write H is equal to V1 square by 2G. So this we shouldn't do. Okay. Now what to do then? We have to use energy balance. See here, net head is input. Net head is input. A part of this input is utilized to give mechanical work. Okay, a part of this input head comes out as a mechanical work, and remaining part will be lost in the form of this kinetic energy. Okay, if draft tube is used, then certain part of this kinetic energy is also recovered. But in the question, it is not mentioned about draft tube. So we are assuming that there is no draft tube. If there is no draft tube, then kinetic energy at exit, that is V2, it is not recovered. This is completely lost. So we'll write energy balance now. This input is equal to output. Output is theoretical head developed by the turbine, that is HE, plus loss is V2 square divided by 2G. So this equation is energy balance. So from energy balance, we are writing this equation. This H is input, HE, this is output, and this is loss. Understood? Now we can simplify this equation now. HE, Euler's head is equal to U1 VW1 divided by G. This is Euler's head plus U1 square divided by, this V2 is U1 by 2 whole square divided by 2G. U1 is equal to VW1 from this velocity triangle. So we'll get this as U1 square by G plus 1 by 2, 1 by 8 into U1 square divided by G. So U1 square by G, I'll take out, into 1 plus 1 by 8. So this will be equal to 9 by 8 times U1 square divided by G. So this is expression for H. Now if we substitute this value of H in this equation, we should get answer. I will substitute that. Hydraulic efficiency is equal to U1 square by G into H value we are substituting as 9 by 8 into U1 square divided by G. If you look at this U1 square will get cancelled, G will get cancelled. So what remains? So we'll get this as 8 divided by 9, that is 0.89. So in terms of percent, this is equal to 89%. Now if you look at this option, so 89% is option D. If you take H equal to V1 square by 2G, if you do that, this is actually mistake. If you do that, then in that case you will get answer as 80%. So many students make mistake here. Even faculty members also have made mistake while solving this question. If you see the old solutions from various coaching institutes, so earlier they used to give solution as 80%. Okay. So if you are not able to solve this question by yourself, don't worry, this only. And no need to worry too much about numericals on hydraulic engines, because as I mentioned earlier, in GATE weightage for this hydraulic machines is very less. Till now on turbines there are only 3 numericals, 2 numericals on Pelton turbine. I am talking about 2007 onwards. two numericals on Pelton turbine and one numerical on Francis turbine. On Kaplan turbine till now there is no numerical. Okay, so this is not correct, but if you do this, in that case you'll get option C. Let us now discuss Kaplan turbine. Kaplan turbine is another reaction turbine. Let us first understand various components of Kaplan turbine. So this one is the spiral casing. On right hand side you can see the cross section of casing is big, left side cross section of casing is small. So this is basically spiral casing. Okay, it is similar to the spiral casing in Francis turbine. So after casing, here this green color we are having guide vanes. These guide vanes are mounted around axis in all directions, similar to the Francis turbine. You can see this diagram. So this is Kaplan turbine runner and these guide vanes are mounted around the axis from all directions. Outside of this guide vane there will be spiral casing. In this diagram spiral casing is not shown. Okay, but first component will be penstock, after penstock spiral casing, after spiral casing guide vanes. In Francis turbine, immediately after guide vane there was runner. If you remember this diagram, in Francis turbine immediately after guide vane there is a runner. There is not much gap between this guide vane and runner. But in Kaplan turbine, between guide vane and runner there is a gap, there is a passage. This passage is turning direction of flow by 90 degree. At the exit of guide vane flow is radial, but at the inlet of runner flow is axial. So this passage, stationary passage, is called swirl or whirl chamber. Swirl or whirl chamber. Okay. So this is called swirl or whirl chamber. So what is its function? We'll see. First we understand various components. So after penstock there is a spiral casing. After spiral casing guide vanes. After guide vanes swirl or whirl chamber. After that there is a turbine runner. Okay. So this is called hub or boss. Hub or boss. On this hub runner blades are mounted around the circumference. So these are the runner blades. Runner blades. Okay. One important feature of Kaplan turbine is these runner blades are adjustable. You can see here a pivot. So around this pivot runner blades are adjustable. So this is a pivot. So entire blade can be tilted around this pivot. Later on I will show one animation also. Okay. So first component is penstock, after penstock spiral casings, after spiral casing guide vanes. So this spiral casing guide vanes, they perform similar function as in Francis turbine. The spiral casing second is guide vanes. Third component is swirl or whirl chamber. Okay. Then after that there is a runner, and after runner there is a draft tube. See here, spiral casing and guide vanes, they perform similar function as in Francis turbine. So whatever is function of spiral casing in Francis turbine, same function is performed in Kaplan turbine also. So no difference here. So these two components are similar to the Francis turbine. Similarly, this draft tube, the function of draft tube in Francis turbine and function of draft tube in Kaplan turbine again same. Okay, so this draft tube we are going to study separately. So one extra component we are having swirl or whirl chamber, and there is a runner. Runner of Francis turbine and Kaplan turbine, they are entirely different. Okay, so we are going to concentrate on component number 3 and 4. Okay, what is function of this swirl chamber now? First of all, this swirl chamber turns the direction of flow by 90 degree, but that is not the only function of swirl chamber. As name indicates, flow inside this swirl chamber is rotating. Okay, it is a whirling flow. That's why it is called swirl or whirl chamber. Whatever these arrows are shown, this arrow only will show overall direction of the flow, but actually flow will be revolving around this axis also simultaneously. So it's a kind of spiral. Now why this is happening, we'll discuss. So what I'm saying is, when water enters into the swirl chamber, so simultaneously it is revolving around this hub. Okay, so while revolving it is coming down. So flow is similar to the vortex flow in the wash basin sink. Have you observed the vortex flow in wash basin sink? When water is passing towards the sink, so while traveling in radial direction, simultaneously it is revolving also. So similar flow is present inside this swirl chamber. That's why it is called swirl chamber. Now why this happens? See here, the guide vanes. In top view, guide vanes will be mounted around the runner. So by red color I am showing guide vanes. Okay, so these are guide vanes, and these guide vanes are not directed towards the axis. Okay, you see here, these guide vanes are mounted around the axis, but they will not be directed towards the axis. They will be slightly tilted. Okay, there this aerofoil is not pointed toward the axis, it is slightly inclined as shown here. Now when water is passing through this guide vane, the flow which leaves the guide vane, it is not directed towards the center. It is having certain different direction. It is inclined towards this radial line. So due to which what happens is, flow is not simply going towards center, simultaneously it is revolving also. Just imagine that you have taken one bucket. Inside bucket you want to fill water. By nozzle you are filling water, but this pipe you are not directing towards center. This pipe you are slightly inclined. So water will be striking on bucket surface, right? And then while falling into the bucket it will revolve also. So that kind of vortex is formed here. So this water will be revolving while going towards center. This is absolute velocity of water. Okay, at the exit of guide vane, this guide vane is stationary component, right? So that's why this velocity measured water measured with respect to guide vane, so this will be absolute velocity V. So this absolute velocity is having two components. So this is radial component and this one is tangential component. Okay, this tangential component is responsible for rotation. If we direct these guide vanes exactly towards axis, then there will not be any tangential component. In that case, you will not get revolving flow. But due to presence of this tangential component, flow is revolving. That's why it's called swirl chamber. And there is one more complexity here. The flow inside this Kaplan turbine is quite complex. So that's why this Kaplan turbine is difficult to analyze. Observe most certain fluid particle. Actually, as I mentioned here, streamline will not be like this. Streamline will be kind of a spiral shown here. Okay, but just for the sake of simplicity, I am showing streamline of this kind. Okay. So here I am taking different positions fluid particle. Let us say here inlet. At inlet, this is exit of guide vane and inlet of whirl chamber. Okay. At the inlet of whirl chamber, how many components of velocity are present? So this is exit of guide vane or inlet of whirl chamber. So here we are having two components of velocity. One is radial, another is tangential. So these components I am showing here. So one component is radial, another component is tangential. So tangential component you will see in top view. So here this component I am showing coming out of plane. Okay. When flow enters inside this swirl chamber somewhere here. So here there is a radial component also, there is a tangential component also. In addition to that, there is axial component also. Okay. So this is axial component. So three components are present. And finally here there is no radial component now. Water is not going to axis now. There are only again two components. One is axial component and another is tangential component. So again I am repeating, at the inlet of whirl chamber, as shown here, there is radial and tangential component. But when water enters into the whirl chamber, there are three components of velocity. One is radial, another is tangential, and there is axial component also. At the exit of whirl chamber, there is tangential and axial component. Now if I consider another path here, okay, another fluid particle, okay. Now initially here all three particles will have same tangential velocity, okay, because here flow condition will be symmetric. So from top to bottom all three particles will have same tangential component of velocity. But when this flow leaves this whirl chamber, these particles are reaching at these new positions. Now here all three particles will have different tangential component of velocity. In other words, I am saying the tangential component of velocity gets redistributed when water leaves this whirl chamber. So tangential component will change from inner radius to outer radius. Now why this is changing? That is because of conservation of angular momentum. Okay. When this particle is traveling through this passage, there is no external torque acting on the particle. Torque will act when this particle comes into contact with this runner. But when it is passing through this passage, there is no external torque. If there is no external torque, then angular momentum of the fluid particle must be conserved. So due to which tangential component of velocity gets redistributed. Okay. See here. Angular momentum of fluid particles is conserved in swirl chamber. So let us say mass of fluid particle is dm. Angular momentum will be tangential component of velocity into r. Tangential component of velocity will indicate by Vw. So this is constant. So this implies Vw is equal to some constant k divided by r. Okay. So remember this relation. So Vw means tangential component of velocity, that is equal to some constant k divided by r. So this equation is called free vortex distribution. Free vortex velocity distribution. Okay. So what does this equation say? At innermost radius velocity is highest and at outermost radius velocity is lowest. velocity is inversely proportional to the radius. Okay. So here if I take this particle, so at this point radius is less, radius is measured from the center, right? So radius is least here. So at this point velocity, tangential component of velocity will be highest, and at outermost point tangential component of velocity will be lowest. So I can say that when we pass, when we travel from inner radius to outer radius like this, so in this direction R value increases. As R value increases, tangential component of velocity decreases. In addition to that, along these points, when we go from inner radius to outer radius, your blade velocity is increasing, because blade is performing circular motion. In circular motion, velocity is R into omega, and this VW will be equal to K divided by R. So what is happening? Tangential component of velocity is inversely proportional to R, and blade velocity is directly proportional to R. So at the inlet itself, all these red points I am taking at the inlet of runner only. So at the inlet of runner itself, at each point these velocities U and VW are different. So due to which what happens is, velocity triangle for Kaplan turbine will be different at different locations. Okay. So at hub velocity triangle will be different, at tip velocity triangle will be different. That's why analysis of Kaplan turbine is difficult. Okay. So till now there is no numerical questions in GATE on Kaplan turbine. Okay. But if you want to perform analysis, what we do is generally we do one dimensional analysis. We take section somewhere, let us say at the middle of radius. So here we will take section at the middle of blade, and at this point we will do analysis. So whenever velocity triangles for Kaplan turbine are drawn, those are not drawn for entire blade. For Pelton turbine and Francis turbine, we draw velocity triangle for entire blade. But for Kaplan turbine, it is not possible to draw a velocity triangle for entire blade. The reason is, from hub to tip velocities are changing, so your velocity triangles will also change. So we will draw velocity triangle only at a particular section, such as mean blade radius. Now where to draw velocity triangle, that thing will be mentioned in the numerical question. Okay. But point of view, I don't expect any numerical on the velocity triangles of Kaplan turbine, but still we are going to discuss this velocity triangle also. Okay. But remember this important point, for Kaplan turbine velocity triangles are different at different radial locations due to these two variation. Blade velocity is directly proportional to radius, and whirl velocity is inversely proportional to radius. Now after this whirl chamber, water enters into the runner. So this is runner of Kaplan turbine. You can see these blades are curved again. Okay. So when this water is passing through this passage like this, momentum of the fluid particle is again changed due to change in direction and magnitude of velocity. In every turbine, working principle is same. Somehow you have to change the momentum of fluid, otherwise you will not get any force or torque. Now here, when water is passing through this passage, magnitude of relative velocity as well as direction both will get changed. So due to which there is change in momentum, and whenever there is change in momentum, you will get force and torque. Now if this is the direction of flow, then this blade will move in this direction. Otherwise, in other words, if you observe from top side, this shaft should rotate in anti-clockwise direction. Okay. So this is how force is generated. After runner, water enters into the draft tube. Working of this draft tube we are going to discuss separately. Now important point here is, for Kaplan turbine, these runner blades are adjustable. These are adjustable. They are not rigidly fixed. Here I will show you animation. You can see here. For Kaplan turbine, these runner blades are adjustable. You can tilt these runner blades. In Francis and Pelton turbine, these runner blades are rigidly fixed. Now what is advantage of this adjustable runner blade feature? Okay. Imagine this is a runner blade. Okay, runner blade section. as we discussed earlier, in order to minimize entry shock, this relative velocity will be tangential, right? This relative velocity should be tangential. If it is not tangential, then you will get entry shock. But we have discussed that to control power output, we have to adjust guide vanes, right? To control power output of turbine, we must control discharge, and discharge is controlled by adjusting guide vanes. When we adjust these guide vanes, the direction of relative velocity will change. Okay, direction of relative velocity will be changed. Now in this particular case, you will get shock and there will be flow separation on opposite side. Okay, it means what? If blades are rigidly fixed, again I am repeating, if blades are rigidly fixed, then shock free entry is possible at only one setting of guide vanes. Okay, that setting is called design setting. Okay, at one particular setting of guide vanes only shock free entry is possible. If you adjust the guide vane, there will be always a shock. Okay, but in Kaplan turbine, if we adjust guide vanes, simultaneously we can tilt this runner blades also. Now if this is the direction of relative velocity, now you can tilt this blade such that again relative velocity is tangential. So for most of the guide vane positions, you will get shock entry. So due to this adjustable blade feature of Kaplan turbine, even your turbine is operating at part load condition. Part load condition means what? Suppose capacity of turbine is 10 megawatt. Okay, but you want to produce only 8 megawatt power. Turbine is designed to produce 10 megawatt, but you want to produce only 8 megawatt power. So this is called part load operation. In part load operation, what we do? We decrease discharge. If we decrease discharge, this direction of relative velocity will be changed because discharge is decreased by adjusting guide vanes. Once you adjust guide vane, direction of relative velocity will be changed. In case of Kaplan turbine, simultaneously we can tilt runner blade also, so that again relative velocity is tangential. So even though your Kaplan turbine is operating at part load condition, it will give good efficiency. But on another side, the cost of Kaplan turbine is high. They are the costliest turbine because of this adjustable blade feature. If blades are rigidly fixed, then such turbine is called propeller turbine. Okay, there is only one difference between propeller and Kaplan turbine. Propeller turbine, fixed blades. Kaplan turbine, adjustable blades. Okay, so due to this adjustable blade feature, Kaplan turbine gives high efficiency or even at part load condition. Fine. Hi students, now we will discuss velocity triangle for a Kaplan turbine. Velocity triangle for a Kaplan turbine is most difficult to understand. It is difficult than steam turbine, gas turbine and pumps and compressor also. Okay, and there are reasons why it is difficult. So in short, I will say those reasons, and after that I will explain those reasons in detail. So why velocity triangles are complex? Because velocity of whirl at inlet, this is not constant along blade. Second is blade velocity at inlet, exit, it is not constant along blade. Okay, so that's why velocity triangles are difficult to understand. Okay, so before going into these details, let us first visualize the flow in Kaplan turbine. Okay, these are the guide vanes. Before guide vane, there will be volute casing. Before volute casing, penstock. So penstock, spiral casing, those parts are similar to the Francis turbine. Guide vane is also similar to the Francis turbine. In Francis turbine, we have seen such kind of guide vanes, but that is observed in top view. Okay, guide vanes will be adjustable. And here this is front view. So let us say this is a guide vane. So in front view you will see that as a rectangle, and if you observe from top side you will see here aerofoil cross section. Okay, and these guide vanes can be tilted about those hinge. You can adjust these guide vanes like this. Okay, working is similar to the guide vanes of Francis turbine. After guide vanes, water will be entering into this passage. This passage is called swirl chamber or whirl chamber, and there is reason behind this name, swirl or whirl. It is called swirl chamber or whirl chamber because flow inside this passage, it is revolving around the axis. Okay, so flow is not simply flowing along passage. While flowing along passage, flow is revolving around its axis also, similar to the vortex in a wash basin. You might have observed vortex in a wash basin. When flow inside a wash basin sink, it starts flowing towards sink, simultaneously it will revolve also. Am I right? Similar flow happens inside this whirl chamber. So while passing along this passage, the flow is revolving also. That's why it is called swirl chamber and whirl chamber. Now why it revolves? These guide vanes are inclined. These are not straight. These guide vanes are inclined. So that's why whenever water is coming along these guide vanes, it will not directly go towards center. It is having one component towards center and one tangential component also. Okay, so this is radial component and this is tangential component. Due to this radial component, water will start going towards center, and due to tangential component, it will revolve around the axis. As these guide vanes impart tangential component, the flow is revolving. Okay. Now there is one interesting thing. If you observe the fluid particles, different positions. Let us say this is 1 and this one is 2. Okay. Fluid particles, initially they are at same radial location, but after some time their radial location is different. Okay. So this is 1 dash, maybe I will use different names. Let us say this is A, this is B, 1 and 2 I have already used. So this is A dash and this one is B dash. Okay. So initially particles A and B, they will have same radius, but sometime radius of B is more than radius of A. As these particles are flowing inside a passage without influence of any external torque, this is simply passage, there is no torque acting on fluid particles. The angular momentum of this particle is conserved, and due to conservation of angular momentum, lesser the radius, more will be the velocity. Okay, we can prove this mathematically also. Angular momentum is moment of linear momentum. So R dm into V, this is angular momentum. Okay, mass of a fluid particle is, let us say, dm. R into Vw, it represents moment of velocity vector, and this has to be constant. Angular momentum is conserved, that's why derivative of angular momentum has to be 0, or we can say R into Vw is equal to constant, or Vw is equal to K by R. This is coming from principle of angular momentum conservation. Okay. Now what is Vw? Vw, you can say this is tangential component of velocity. Vt and Vw are same thing. Tangential component is whirl component. Okay. So whirl component follows free vortex distribution. So whirl component is inversely proportional to the radius. This is called free vortex distribution. Okay. So particle which is nearer to the hub, it will be revolving faster, and particle which is away from the hub, it will be revolving slower. This is called free vortex distribution. This is for tangential component of velocity. Okay. As this tangential component is different at different points, even though all those points are at inlet, am I right? All those points are at inlet, but at each point tangential component will have different velocity. That's why at each location velocity triangle will be different. Okay. Another complexity here is, if you observe this blade velocity u is equal to r into omega. Okay. At inlet different points have different radius, so that's why blade velocity is also different. So u at inlet u is equal to r1 into omega. So u1 we can say it is directly proportional to r1. Okay. So velocity of whirl at inlet. Okay, one is for inlet because we are analyzing this flow up to inlet. So velocity of whirl at inlet will follow free vortex distribution, and blade velocity is directly proportional to the radius. Please remember these two important points. Okay. Blade velocity is directly proportional to the radius and whirl velocity is inversely proportional to the radius. So due to these two things, velocity triangles of a Kaplan turbine are complex. Why complex? Because at each point these values will be different. So you have to draw separate velocity triangle at each location. If you want to design this Kaplan turbine blade, so at each radial location you have to draw different velocity triangle. But one good thing is we can make elementary analysis by considering any one of the velocity triangle. So for the analysis purpose, velocity triangle is mostly drawn at mean blade radius somewhere here, or blade tip, or at hub. These are three popular choices where velocity triangle is generally drawn. Where to draw velocity triangle, this point will be mentioned in the question. So you have to read the question carefully, from that you can understand where to draw this velocity triangle. Okay. Now whenever we want to draw velocity triangle for a Kaplan turbine, so first you have to select the location. As I mentioned earlier, at each radial location, that is at tip, mean blade radius, or hub, or any radial location, blade velocity and whirl velocity are different. That is why velocity triangles are different. We have seen this. Whirl velocity at inlet is inversely proportional to r, and blade velocity at inlet is directly proportional to r. So due to this, velocity triangles will be different at each radial location. So first you have to select radial location, and where to select radial location, this thing will be mentioned in the question. Let us say I want to draw velocity triangle at mean blade radius at this location, okay, at the middle of the blade. Okay. So what you have to do, first you have to take one cross section here. If you cut blade at this point, and if you have the sectional view from the side, you will see cross section. Okay. So imagine that, so this thing is one of the blade which is coming out of plane, and at the middle you have taken section. So you will see the similar cross section. Okay. So same cross section I am showing here. This is cross section of a blade at mid radius. Please remember, this is not entire blade. In case of Francis turbine, we used to draw entire blade. This is not entire blade, it is just section of a blade. Okay. We are taking section here and observing from this side. So you will see a cross section. Okay. This cross section will be moving with velocity equal to r into omega. Okay. Imagine that blade is coming out of plane like this. So you have taken a section here. At this point, the blade will be going towards right. Angular velocity, it is in this direction, so blade is going towards right. So that is why here u1 is equal to u2 and it is equal to r into omega. Why u1 is equal to u2? Because we are taking cross section at a particular radius. So at inlet as well as at exit, radius from this axis is same. As r1, as r is same, blade velocity is same. Okay. And this is equal to r into omega. If I am taking cross section at the middle of blade, then you should take this as mean blade radius. Okay. So first step is to show direction of blade velocity, and at inlet as well as exit, blade velocity will be same. Whenever you want to draw velocity triangle, we have seen always we have to show relative velocity, and the direction of relative velocity is tangential to the blade. Relative velocity at inlet, that is why VR1. Similarly, relative velocity at exit, it will be tangential to the blade. So this is VR2. Understood? So these velocity vectors you should draw first. Why relative velocity at inlet is tangential? To avoid entry shock, and at exit flow is forced to follow this curvature, that is why VR2 is tangential. Now into this relative velocity we should add blade velocity. The basic principle is same. We have seen absolute velocity vector is sum of blade velocity and relative velocity. So in relative velocity I have to add blade velocity. Let us say blade velocity is at inlet is u1 and blade is going towards right. So I have added this velocity here. Relative velocity plus blade velocity, I will get absolute velocity. So by triangle law, resultant vector will start at starting point of first vector and it will end at end point of second vector. So this is v1. Similarly here, blade velocity I will add at the exit u2. There is u1 and u2 are same. So you should draw these vectors roughly of same length. And this is v2. This angle alpha 2 is again 90 degree. The reason is same as that of Francis turbine. To minimize the loss, v2 must be minimum, and minimum value of v2 you will get only when this triangle is right angle triangle. So here vw2 will be 0. vw2 is tangential component and v2 is equal to vf2. Okay. So if you show the angles, this angle made by absolute velocity with blade velocity, it is alpha 1, and angle made by relative velocity with blade velocity is beta 1. Okay. With our convention we will show always angles on interior side of triangle, and now we will show whirl and flow velocity. This is velocity of whirl at inlet, that is why vw1, and this distance will velocity of flow at inlet, that is why vf2. Okay. Now we will show that in case of Kaplan turbine always vf1 is equal to vf2 and its value is 4 times of discharge divided by pi dt square minus pi dh square. Okay. This result will show later. So here what is dt, what is dh, I will explain later. But please remember, once in the question it is mentioned a Kaplan turbine, for Kaplan turbine always u1 equal to u2. Why u1 is equal to u2? Because we are taking velocity triangle at a particular section, that is why u1 is equal to ut, and always vf1 is equal to vf2. So by default these conditions will be true, no need to mention these conditions separately. For Kaplan turbine always you take u1 is equal to u2 and vf1 is equal to vf2. Okay. So this angle will be beta 2, angle between relative and blade velocity, this is beta 2. Okay. So this is velocity triangle. Now what is complexity here? The complexity here is, if you want to design Kaplan turbine blade, okay, so these blade angles, this depends upon velocity triangle, am I right? So these blade angles will be different at different radial location. At each radial location blade angles are different. Why different? Because at each radial location u is different, because u is directly proportional to r, and at each radial location vw1 is also different because vw1 is inversely proportional to r. So these triangles are going to have different shapes at each radial location. Okay. This makes analysis of Kaplan turbine complex. So if you want to design blade, you have to draw velocity triangles at several sections, then you calculate blade angles and then accordingly you design blade. That is why if you see the blade of Kaplan turbine, it is twisted, it is not a flat blade, it is a twisted like a blade of a fan. Have you seen the blade of a fan, ceiling fan? The ceiling fan blade is twisted. Similar to that, Kaplan turbine blade is also twisted. Okay. I hope you understand this Kaplan turbine velocity triangles. But one good thing is, even though velocity triangles are different, we can use basic formula like hydraulic power, torque, again hydraulic efficiency. These formulas will give same value. We will discuss this point later. Hello students, let us see now how to find out discharge passing through the Kaplan turbine runner. So first formula comes into mind is discharge is equal to flow area into velocity of flow. Okay. Now we should understand what is flow area and what is velocity of flow. Okay. Flow area, if you observe this runner, flow area is area bound between two cylinder. One is outer cylinder is casing of turbine, and inner cylinder is hub. So area between casing and hub is flow area. So area bounded by two cylinders, if you see in top view, area bounded by two cylinders is a flow area. So this is shape of flow area. Okay. So it is annular circular area. Outer diameter of this area, outer diameter will be equal to blade tip diameter, and inner diameter will be equal to hub diameter. So that's why AF1, which is also equal to AF2, AF1 and AF2 at inlet section is section 1,1, exit section is section 2,2. Both sections will be having same area, and its value is pi by 4 dt square minus dh square. Okay. What is dt here? dt is blade tip diameter and dh is hub diameter. Hub diameter. I hope you are able to visualize this flow area. Now, as AF1 and AF2 are same, VF1 must be equal to VF2. This is equal to Q divided by flow area. Flow area is AF1, AF2, and flow area is pi by 4 into dt square minus dh square. So VF1 is equal to VF2, 4 times of Q pi dt square minus dh square. Okay. So this is formula for discharge. Please remember this formula. This is important formula. Most of the formulas for Kaplan turbines are similar to the Francis turbine. Only 3 formulas are slightly different. Out of those 3 formulas, this is the first one. Please remember this formula. All other formulas for Kaplan turbine and Francis turbine are exactly same. For example, formula of torque. Torque generated by runner. Okay. So if you remember, for Francis turbine, the formula was torque is equal to rho Q into VW1 into R1. This formula was derived based upon Euler turbine equation. So VW2 is again 0. Then formula for runner power. Power developed by runner. Runner power. This formula is equal to runner power is equal to torque into angular velocity. So you'll get rho Q VW1 into U1. Okay. So this formula is exactly same. Hydraulic efficiency formula. Eta H is equal to VW1 U1 divided by G into H. So all formulas, all remaining formulas are same. One important thing to note here is, in case of Kaplan turbine, we are drawing velocity triangle at a particular radial location, such as mean blade radius, tip or hub. Okay. So even though you can change radial location, if you change radial location, definitely U1 value, VW1 value, U1 values will be different. Okay. But interesting thing is, for all radial locations, value of torque, run power and hydraulic efficiency, these 3 values will be exactly same. even though you change the location. Now why it has to be same? We have seen VW1 is inversely proportional to R. If this is the case, then product of VW1 into R1 is constant. If this is constant, then torque has to be constant. So even though you change the radial location, torque value will be same. Similarly, if you observe this formula, runner power is equal to rho Q VW1 into U1. We have seen U1 is directly proportional to R. Therefore, VW1 into U1, this product should be again constant. Okay. VW1 is inversely proportional to R1 and U1 is directly proportional to R1. So this product has to be constant. So runner power is also constant. Similarly, hydraulic efficiency is also constant. Okay. So if you change the radial location, shape of velocity triangle will change. So its practical implication is blade angles will be different. So blade has to be twisted. But torque, runner power or hydraulic efficiency obtained from velocity triangle at any radial location will be exactly same. Please remember this point. The formulas for various efficiencies and different losses for Kaplan turbine and Francis turbine are again same. If you remember our discussion of Francis turbine, the highest power available was hydraulic power. Energy from water, it is being converted into mechanical energy. Okay. So highest power is power of a water, that is called hydraulic power. Out of that hydraulic power, some energy is lost. Remaining power is converted into mechanical work, that is called runner power. The power developed by runner entirely it is not transferred to the generator because some power is lost due to various mechanical losses. The final power which is transmitted to the generator, it is called shaft power. Okay. The difference between hydraulic power and runner power is hydraulic losses. Hydraulic losses means losses which are related to water. So when water is flowing through the turbine, there will be fluid friction, okay, or there can be shock loss also. Those are called hydraulic losses. And the bearing friction, that is called mechanical loss. Okay. Between hydraulic power and runner power, which efficiency is defined? If you remember our earlier discussion here, hydraulic efficiency defined, and between runner power and shaft power, mechanical efficiency is defined. Hydraulic efficiency considers hydraulic losses, mechanical efficiency considers mechanical losses, and all the losses are considered by overall efficiency. Okay. So the formula for hydraulic efficiency, I will write first. Hydraulic efficiency, eta suffix h, eta h is equal to runner power divided by hydraulic power. Runner power is rho q VW1 U1, hydraulic power is rho g QH. So eta h is equal to VW1 U1 divided by GH, exactly same as Francis turbine. Second formula, this is for mechanical efficiency. Mechanical efficiency, it is defined as eta suffix m. Eta suffix m is equal to SP divided by shaft power divided by runner power. Okay, runner power is power developed by the runner, how much work runner is developing. SP is actual power transmitted to the generator. Overall efficiency, overall efficiency is defined as SP divided by HP. So this you can rearrange as RP divided by HP into SP divided by RP. So overall efficiency is equal to, first term is hydraulic efficiency and second is mechanical efficiency. Okay. So these formulas are exactly same as that of Francis turbine. Only three formulas are different, which I mentioned earlier. One is formula for discharge, second is formula for speed ratio, and third is formula for flow ratio. These formulas are different. All other formulas for Francis turbine and Kaplan turbine are exactly same. The second formula which is different in Kaplan turbine as compared to Francis turbine is speed ratio. Speed ratio notation for this is Ku. Okay. If you remember the definition of speed ratio in Francis turbine, it was defined as U divided by root 2gh. In case of Francis turbine, this U is taken as U1. For Francis, it was taken as U1. U1 means blade velocity at inlet. Okay. But for Kaplan turbine, there is problem, because for Kaplan turbine, we can draw velocity triangle at different radial locations. So if you change the radial location, U1 value will be changed. So all those points are at inlet only. Am I right? This is entire section is inlet. So everywhere at inlet, blade velocity is different. So that's why for Kaplan turbine, U is defined based upon blade tip velocity. Please remember this. Speed ratio is defined based upon blade tip velocity, because U1 value is different at different radial locations, even though inlet is same. Okay. Now, second formula which is slightly different is flow ratio. Sorry, this is third formula which is different is flow ratio, Kf. So definition of Kf is similar. Kf is defined as Vf divided by root 2gh. So for Francis turbine, if you remember, it was taken as Vf1, but for Kaplan turbine, Vf1 is equal to Vf2. So everywhere at inlet as well as at exit, Vf1 equal to Vf2, and this is equal to 4 times of Q divided by pi by 4 pi into dt square minus dh square. Okay. As flow velocity is same, you can take here anything. So Vf may be equal to Vf1 or Vf2. So anything you can take, that is okay. Okay. And the ranges are also different. As we discussed earlier, the speed ratio and flow ratio, those are function of only geometric shape. So they will vary with respect to geometry. So for Kaplan turbine, the range of speed ratio is 1.3 to 2.3. And for flow ratio, this range is 0.35 to 0.75. Again, no need to remember these ranges, just typical values I am giving. What you should remember is this definition. For Francis turbine, speed ratio is defined based upon U1. For Kaplan turbine, it is defined based upon tip speed. Okay. For Pelton turbine, U1 again is equal to U2. So anything you can take. So for Kaplan turbine, this numerator is taken as bucket speed. For Pelton turbine, for Pelton turbine, it is taken as bucket speed. For Kaplan turbine, it is defined based upon tip speed, and for Francis turbine, it is defined based upon U1. Flow ratio for Pelton turbine is not defined. Flow ratio is defined only in case of Kaplan turbine and Francis turbine. For Francis turbine, you can take this Vf as Vf1, and for Kaplan turbine, anything you can take. Hello students, read this question. This is numerical problem on Kaplan turbine. It is not asked in GATE. In GATE till now there is no numerical on Kaplan turbine. So this is simple numerical which I have designed. In a Kaplan turbine runner diameter, in a Kaplan turbine, runner diameter is 3 meter. Runner diameter is 3 meter. So try to understand given data. Runner diameter is 3 meter means outer diameter is 3 meter. Okay. Outer diameter of runner, size of runner is given 3 meter, and hub diameter is 1 meter. Hub diameter means inner diameter. Okay. So dh is equal to 1 meter. Okay, so this is tip diameter also. Outer diameter is blade tip diameter, and hub diameter we can say it is inner diameter also. Okay, fine. If the velocity of flow and peripheral velocity of the blade tip on inlet side of the blade are 5 meter per second and 25 meter per second. Velocity of flow means Vf and peripheral velocity. Peripheral velocity means tangential velocity. Peripheral velocity of blade is saying tangential velocity of blade, not water. Okay, so it means it is U on the inlet side of the blade. Inlet side means 1. Vf1 and U1, where at blade tip. This is also at tip. So these are 5 meter per second and 25 meter per second. What is asked? Then the discharge through the runner in meter cube per second. Discharge he is asking. What is formula for discharge? Discharge equal to flow area into velocity of flow. Correct? In case of Kaplan turbine, flow area is annular circular area. So this is equal to pi by 4 into dt square minus dh square. This is flow area. At inlet as well as exit, flow area remains same, and velocity of flow is same everywhere. So whether you calculate velocity of flow at tip or hub or at inlet or at exit, everywhere velocity of flow is same. So simply I am writing Vf. So everything is given. Pi by 4 dt is 3 square minus 1 square. Velocity of flow, this is given as 5. So this 25 meter per second, this is blade tip velocity. It is not required. This is redundant data just to confuse you. So this is equal to pi by 4 into, this will be 9 minus 1, 8 into 5. So this is 2, 5 into 2, 10. 10 pi meter cube per second. So that is 31.4 meter cube per second. So if you know the formula and if you understand the meaning of these terms, this question is very simple. So such questions may be expected on Kaplan turbine in GATE. Hello everyone, let us have a look at this question. This is another numerical on Kaplan turbine which we have designed here. First, try to understand the given data. A Kaplan turbine develops 14 megawatt of shaft power. So SP is given 14 megawatt under net head of 14 meter. So net head means H. H is given 14 meter. At speed 150 RPM. So operational speed is given 150 RPM. Speed ratio, flow ratio and hub to tip diameter ratio are 3.6 and 0.4. So 3 ratios are given here. First is speed ratio. Speed ratio means Ku. This is given as 2. Then flow ratio means Kf. This is given as 0.6. And hub to tip diameter ratio, that is dh divided by dd, hub diameter to tip diameter ratio, this is given as 0.4. Okay, what do we have to find out? Find overall efficiency of the turbine. This overall efficiency we have to find. Okay, now what is formula for overall efficiency? Overall efficiency is equal to SP divided by HP, shaft power divided by hydraulic power. Shaft power is given here. hydraulic power we can write as rho g QH. So in this equation, if you observe, A is given and head is given. So somehow we have to find out discharge. What is formula for discharge? How to get discharge? Discharge is equal to AF into VF, and AF is equal to pi by 4 dt square minus dH square into VF. Okay. So if you get discharge and if you substitute in this equation, we should get expression for overall efficiency. Let us say this as equation number 1 and this as equation number 2. So in equation number 2, dt, dH both are unknown, VF is also unknown. Okay. First we will get this VF based upon this flow ratio. So what is definition of flow ratio? KF is defined as VF divided by root 2 GH. So this is definition of flow ratio. So head is given, from here we'll get velocity of flow. So VF is equal to KF into root 2 GH. Now substitute the values. KF is 0.6 into square root of 2 into 9.81 into H is 14 meter. If you substitute these values and if you do the calculations carefully, you should get value of velocity of flow as 9.94 meter per second. So velocity of flow is known. dH, dt we have to find. Here diameter ratio is given, dH by dt is given, but before that we should know one diameter, either dt or dH. Now how to get this diameter? You can pause this video, this is the critical step. Once you understand how to find out diameter, any one of this diameter, our problem is solved. Now I am giving you solution for this. See here, this speed ratio we have not used. Okay, so speed ratio is related to the blade velocity, am I right? So I am going to next slide. Definition of speed ratio for Kaplan turbine is blade tip velocity divided by root 2 GH. So that is UT is equal to KU into root 2 GH. This UT we can write in terms of diameter. So UT is equal to blade tip velocity is equal to pi dt into n divided by 60 into KU into root 2 GH. Now look at this equation now. So in this equation dt we have to find pi 60 n value is given, KU is given, G known, H is also known. So only unknown is dt. Now substitute the values. Pi into dt, n value is 150 rpm divided by 60. Let me check n value. Yes, 150 rpm. KU is 2 square root of 2 into 9.81 into 14. Now if you do these calculations, you should get dt around 4.22 meter. Okay. Now from dt we can find out now dH. The diameter ratio is given, dH divided by dt. So this ratio is given as 0.4. Therefore dH will be equal to 0.4 into 4.22. You should get this around 1.69 meter. Now substitute this equation number 2. These values you substitute in equation number 2 here in the expression for discharge. Okay, everything is known now. From equation number 2, Q is equal to pi by 4, outer diameter is 4.22 square minus inner diameter is 1.69 square into velocity of flow 9.94. To do this calculation, you should get 116.7 meter cube per second. This you should get value of discharge. Now substitute in equation number 1. In equation number 1, you see here, overall efficiency is equal to SP divided by rho G QH. SP is given. So overall efficiency, SP is given 14 megawatt divided by rho G is 9810. Discharge is 116.7 into head is 14 meter. So this you should get as 0.873. In percentage he is asking up to 1 decimal place. So answer you should enter as 87.3. Okay. So here you should enter 87.3. Let us discuss similarity law. Similarity law is very important topic exam point of view. Many times in GATE as well as in ESC, question comes on this topic, similarity law, directly. Now what is similarity law? We will discuss. Similarity laws are used in model testing. You may be knowing that actual turbines are very big, and to conduct tests on those turbines is costly. That's why what we do is we make small geometrical replica of turbine and will conduct test on that replica, so that your testing will be cost effective. It will be conducted in less time as well as it will be cost effective. That is all idea behind model studies. So this is actual prototype. See, during this discussion we will consider model studies related to the Pelton turbine only and will derive similarity laws. But those same similarity laws we can extend to all other turbines as well as centrifugal pump. Please remember, we are deriving laws for Pelton turbine, but those laws are valid for all turbines as well as centrifugal pump. Okay. So this is velocity triangle for a prototype turbine, and this one is velocity triangle for model turbine. Prototype means actual turbine. So this is actual product. Model means replica. Okay. So model will be small size as compared to the prototype. In order to have some relations between results of model and results of prototype, these models and prototype should satisfy certain conditions. Those conditions are known as homologous condition. Okay. We say that model and prototype are operating under homologous condition when they satisfy these two conditions. First condition is model and prototype should be geometrically similar. It means their shape must be same. This is first condition. Second condition is their velocity triangles are also similar. Shape of the velocity triangle is also same. When these two conditions are satisfied, then it can be shown that results for model and results for prototype will be proportional to each other. Okay. One more thing to note here is, even the model is smaller than prototype, velocity triangle for model need not to be smaller. It can be having bigger size. Only thing is their shape must be same. Is it clear? It means scale ratio for velocity and scale ratio for size need not to be same. Only shape must be same, geometric shape as well as shape of velocity triangle. And these two conditions are satisfied, we say that model and prototype are running under homologous condition. Okay. Now let us understand the implication of this homologous condition. When we say that model and prototype are geometrically similar, in that case all dimensions, linear dimensions, are directly proportional and all angular dimensions must be same. For example, let us say dm is jet diameter of model and dp is jet diameter of prototype. If this ratio is ratio of one of the linear dimension, So this ratio must remain same for all linear dimensions. For example, dm is wheel diameter for model and dp is wheel diameter for prototype. So this ratio again must be same. This condition or this ratio, length ratio LR, we can say length ratio LR, it must be same for all linear dimensions. Understood? So in short, we can say that D is directly proportional to capital D. Okay, if ratio is same, then the variables are directly proportional. Am I right? From similarity of velocity triangle, we can write from second condition, all velocities must maintain same ratio. What is this first velocity? The velocity which is tangential, this velocity as well as this, it must be relative velocity. At inlet, that's why 1. This is relative velocity, at exit, that's why 2. In relative velocity, we are adding which velocity? We are adding bucket velocity. So here bucket velocity, and finally this is absolute velocity. Okay. If triangles are similar, then velocities also must maintain same ratio. So from second condition, we'll get, this is from first condition. From second condition, we'll get VR1 for model divided by VR1 for prototype is equal to U1 for model divided by U2 for model, and so on. For each velocity, you can write this, that is equal to jet velocity of model divided by jet velocity of prototype. So this ratio you can write for all velocities. What is formula for jet velocity? Jet velocity is CV into root 2 GH. Okay. So we can say that Vm is directly proportional to root h. So Hm divided by Hp, because V is equal to root 2 GH, CV into root 2 GH. One more thing is, in the model studies, we neglect effect of friction. So CV we are taking as a 1 because effect of friction is ignored. Understood? So in short, we can say that from second result, any velocity, be it relative velocity, jet velocity or bucket velocity, any velocity is directly proportional to root h. So from first condition, we are getting any dimension is directly proportional to diameter of wheel, and from second condition, we are getting any velocity is directly proportional to root h. I hope you understand this. Okay. So what is formula for bucket speed? Bucket speed for Pelton turbine is pi d n divided by 60. Just now we have seen that any velocity is directly proportional to root h. So u is also directly proportional to root h. So I can say u is equal to pi d n divided by 60. So nd is directly proportional to root h. This is first similarity law. 3 simple relations will get based upon these 2 conditions. First condition we got is any dimension is directly proportional to capital D. Second condition is any velocity is directly proportional to root h. So what is meaning of this? N1 D1 divided by root h1 is equal to N2 D2 divided by root h2, and so on. This is constant. If there are suppose n hydraulic turbines, n similar hydraulic turbines which are operating under homologous condition. So instead of simply one model and prototype, there are suppose n machines, and if they are operating under homologous condition, then this constant, this ratio must be constant, and this is called head coefficient, CH. CH is head coefficient. Similarly, we can derive relation for discharge also. What is formula for discharge? For Pelton turbine, discharge equal to jet area into jet velocity. Jet area is pi by 4 small d square, pi by 4 into small d square, and jet velocity is root 2 gh. Remember, effect of CV we are ignoring. So we can say that discharge is directly proportional to small d square into root h, and small d is directly proportional to capital D. Any dimension is directly proportional to the wheel diameter, that we have seen. So d square into root h. This is second similarity relation. Second relation we got is discharge is directly proportional to d square into root h. This is second similarity law. Okay, so you should remember those laws, very important laws. First law is nd directly proportional to root h. Second is q is directly proportional to d square root h. So from here again, if there are n machines operating under homologous condition, then q1 divided by d1 square into root h1 should be equal to q2 divided by d2 square root h2 and so on. This constant ratio is called discharge coefficient, CQ. Discharge coefficient. Okay. So even if you forget names of this coefficient, it doesn't matter, but what you should not forget is this relation. Discharge is directly proportional to d square h, d square into root h, and this is very easy to derive also. We are deriving all those equations from very simple two laws. First law is any dimension is directly proportional to diameter, and second is any velocity is directly proportional to root h. Based upon these two we are deriving this. So we can easily derive this, no need to mug up these formulas. Okay. Next is power. Power is equal to overall efficiency into rho g QH. It can be shown that if machines are operating under homologous condition, then their efficiency remains same. Efficiency is function of velocity triangle. This you can judge. This you can try as a homework. Efficiency of two machines which are operating under homologous condition, it is same. Efficiency is related to the velocity triangle. I will just give one hint. In case of Pelton turbine, maximum efficiency is obtained under which condition? U by V equal to 0.5. Am I right? At this condition, maximum efficiency is obtained. If for model U by V is 0.5, then for prototype also U by V should be 0.5. It means if model is operating at maximum efficiency, prototype also must operate at maximum efficiency. So their efficiencies will be same. For other values of U by V, again efficiency will be same. You can work out this as a homework. Efficiency of two machines which are operating under homologous condition is exactly same. Okay. So we can say that power is directly proportional to Q into H, and Q we have seen it is directly proportional to d square root h into h. So power is directly proportional to d square into h to the power 3 by 2. Okay. This is third similarity law. These three are very important relations. From here we can write for n machines as, suppose there are n machines which are operating under homologous condition. P1 divided by d1 square h1 to the power 3 by 2 is equal to P2 divided by d2 square h to the power 3 by 2 and so on. This is called power coefficient Cp. Cp is called power coefficients. Okay. And these coefficients will have unique value when turbines are operating under given homologous condition. For example, suppose for Pelton turbine U by V is equal to 0.5. For this 0.5 ratio, value of Cp, Cq, Ch, this will be same for all n machines. Those terms will be same. But if I change this U by V from 0.5 to 0.4, then these coefficients will again have different value. But at a given conditions, at a given shape of velocity triangle, we can say that these coefficients are same. we have derived formula of head coefficient, discharge coefficient and power coefficient. This formula we have derived using homologous condition. The meaning of homologous condition is geometric shape is same and shape of velocity triangle is also same. Okay. So we can say that CH, CP and CQ, it is function of geometric shape of a machine and shape of velocity triangle. As long as these two things are same, these coefficients will have same value, but if any one of them changes, then these coefficients will have different value. Okay. Now let us discuss speed coefficient, specific speed. The formula for specific speed is derived using these similarity laws only. From first formula we can eliminate d, so we can write d is equal to ch into root h divided by n, and we can substitute this value of d in the equation of Cp. So we'll get Cp equal to P divided by d value is ch root h by n whole square into h to the power 3 by 2. So we can rearrange this. N square into P divided by h to the power 5 by 2 is equal to Cp into Ch square. Am I right? Okay. That is P n root P h to the power 5 by 2 is equal to Ch into root Cp. So for a given homologous condition, these coefficients are constant. So this is also equal to constant, and this constant is called speed coefficient. Cs is speed coefficient. And this is 5 by 4. Fine. So this formula looks exactly same of formula of specific speed, but there is slight difference between speed coefficient and specific speed. There is a conceptual difference. Please understand this difference. Okay. So we have derived those coefficients under homologous condition. Under homologous condition, these two parameters must be same. So we can say that speed coefficient value is also constant under homologous condition. So speed coefficient is also function of geometric shape and shape of a velocity triangle. You can think in this way. Even though geometric shape of a hydraulic turbine is same, but by operating turbine under different condition, you can change shape of velocity triangle. For example, u by v equal to 0.5 will give different shape. U by v equal to 0.3, it will give different shape of velocity triangle. Okay, and for these two conditions, Cs values will be different. Understood? So speed coefficient depends upon shape as well as shape of velocity triangle. Specific speed, it is denoted by Ns, and it is a special case of speed coefficient. What is speciality? Among infinite values of those speed coefficient, please remember, for each geometric shape you are getting one value of speed coefficient. Among infinite value of those speed coefficient, there will be one value of speed coefficient for which efficiency of the turbine is maximum. In case of Pelton turbine, we will get maximum efficiency at u by v equal to 0.5. The speed coefficient corresponding to this is called specific speed. Okay. So specific speed is a special case of speed coefficient. What is the speciality? You should consider speed coefficient at maximum efficiency, and that is called specific speed. So formula wise it is same, but we should remember that specific speed is always calculated at maximum efficiency. So Ns is equal to, formula is same, but this you have to always calculate at maximum efficiency of machine. Okay, that's why people say that specific speed is the speed of a geometrically similar machine. Why geometrically similar machine? Because these conditions are derived under homologous condition. I hope you remember the equation. We have taken n different types of machine. So among that different types of machines, one machine will have head equal to 1 meter and power equal to 1 kilowatt. So corresponding speed will be specific speed. Okay, but that definition will not give some meaning. Whatever we have discussed, from that you can understand specific speed in this way. Okay, under given homologous conditions, CH, CQ and CP are constant, and these are just proportionality constant. And specific speed is special case of speed coefficient. This is also proportionality constant, but NS is special case of CS. What is speciality? At CS, at NS, efficiency is maximum. Now we can say that the specific speed is function of only geometric shape. These coefficients are function of geometric shape as well as shape of velocity triangle, but for specific speed, shape of velocity triangle is unique. That is not a variable. We have to consider only one velocity triangle at which efficiency is maximum. That's why people say NS is function of only geometric shape. Because at maximum efficiency condition, shape of velocity triangle will be unique. I hope you understand now physical significance of specific speed. Let us discuss now how specific speed is used to select turbines. This is important concept and many students will have confusion regarding this. Selection of turbine is always based upon specific speed. If you remember, we have already discussed that specific speed is a function of only geometric shape. The speed coefficient depends upon geometric shape as well as shape of velocity triangle. But as specific speed is always calculated at maximum efficiency, and maximum efficiency will get only at unique velocity angle, that's why specific speed is purely function of geometric shape. Then depending upon geometric shape, specific speed can change. For a given geometric shape, if size is changing, specific speed will not change. For selection of turbines, this graph is utilized. Let us see what does this graph represent. On x-axis of this graph, there is a specific speed, and on y-axis, maximum efficiency of the turbine. Okay. For example, if you consider a particular geometry of a Pelton turbine, let us say it is having some 20 buckets, bucket angle is let us say 15 degree, and so on. Let us say there is a particular geometry. For a particular geometry, specific speed will have unique value because specific speed depends only upon geometric shape. So we'll get only particular unique value of specific speed, and particular geometry will have unique value of maximum efficiency. So we'll get 1 point on this graph. Now you can keep on varying shape of turbine. Instead of 20 buckets, you can take 25 buckets. Your geometry changed. You get different blade angles. Again, geometry changed. So for another geometry, you will get another value of specific speed, and the next geometry will have different maximum efficiency. So that value will be somewhere, let us say here. In similar fashion, you can keep on varying geometries of Pelton turbine. So various configuration of Pelton turbine you can study, and you can plot their efficiency versus geometric shape. So you'll get a graph. In fact, to get this graph, extensive testing is required. So this graph is obtained after testing, because you need to test each and every possible combination of particular turbine. So after testing various configuration, you will get graph for Pelton turbine. Similarly, you can consider Francis turbine. By different configurations of Francis turbine, you will get different graph. Similarly, get another graph for Kaplan turbine. Okay, and these graphs are obtained after extensive testing, and the selection of turbine is done based upon this graph. Now let us discuss what does this point represent. The topmost point represent highest efficiency, but if you see y-axis, already we have maximum efficiency. So what is the meaning of this point? This point indicates that this particular geometry of a Pelton turbine will give highest possible efficiency. Please remember, two different shapes of geometry need not to have same efficiency. For example, maximum wheel efficiency of Pelton turbine, if you remember, the formula is 1 plus k cos beta 2 divided by 2. So if I change geometry, blade angle can change, so efficiency will be different. So this formula says that for different geometries you will have different maximum efficiency. So this particular point indicates best possible configuration of Pelton turbine. No other configuration of Pelton turbine will give better efficiency than this. Similarly, this point indicates best possible configuration of Francis turbine, and so on. Okay. Now let us come to the selection part. If you remember the formula of specific speed, Ns is given as N root P H to the 5/4, where N is rotor speed, P is power in kilowatt, and H is head in meter. The value of specific speed we can calculate in advance based upon data available. For example, based upon level of water available in dam, H value you can judge. So this H value you can take approximate guess. So based upon head available inside reservoir. So head available inside reservoir is gross head, H here is net head, but both will have nearly same value. So you can at least make some approximate estimate of H. Power of the turbine you can decide, like you want 1 megawatt turbine or 2 megawatt turbine or 10 megawatt turbine, that you can decide based upon how much quantity of water is available inside reservoir. So you can have estimate of capacity of reservoir over a period, how much over a period of let us say 1 year, how much water it can supply. Based upon that, the power value of turbine you can decide, power output of turbine you can decide. So this is based upon quantity of water available. Quantity of water available. Then N is runner speed. If you remember, this runner speed is directly related to the frequency of AC. So frequency of AC is fixed. Am I right? Frequency of AC in India is 50 Hz. So it is fixed. Runner speed and frequency of AC is this relation. Frequency is equal to pair of poles into speed divided by 60. So if frequency is fixed, runner speed will be fixed. So based upon availability of gearboxes and type of turbine, this runner speed will be fixed. So this you cannot change. So this is based upon gearbox and type of. So based upon this you can have some rough value of N. Once you fix these parameters, you will get some specific speed value. Okay. Now by taking this value, you can look at this graph. For example, suppose this specific value falls somewhere here. Okay. The calculated value of specific speed you can look on this graph. Let us say it is falling somewhere here. Now for this specific speed, Francis turbine gives maximum value. So this particular geometric shape you have to select. Suppose forcefully you want to use their Pelton turbine. People say, what happens if I use Pelton turbine? Okay, you can see from the graph, if you forcefully use Pelton turbine, the Pelton turbine at this point will give very low efficiency. Okay, so you will get less power output. So that is not recommended. You can take, let us say, another point. Suppose specific speed is falling somewhere here. So at this point, Kaplan turbine gives this much efficiency, Francis turbine gives this much efficiency. Okay. If both efficiency values are close enough, then you can select turbine whichever suits you. For example, Kaplan turbine is little costly because it is having adjustable runner vanes. That's why it is costly. So if these two values are close enough, then you can go with Francis turbine also, because both efficiencies are nearly same. So that's why you might have observed in the tables, specific speed ranges will be overlapping. It means some speed, for some speed, even Francis turbine you can select and Kaplan turbine also you can select. Okay. If you observe these graphs, Pelton turbine will be having slightly less efficiency as compared to Francis and Kaplan. Based upon this table, many times objective question is asked in the exam, such as Pelton turbine is which type of turbine, whether it is impulse type or reaction type. So Pelton turbine is definitely impulse turbine because there is an impact of jet happening over there. Mainly the reaction and impulse, those are classified based upon pressure. In case of Pelton turbine, pressure inside the runner is atmospheric pressure, and in case of Francis and Kaplan turbine, pressure inside the runner changes. So that's why those are reaction turbine. Pelton turbine is having tangential flow direction, means jet is striking tangential to the wheel, that's why it is tangential flow. Francis is radially inward and Kaplan is axial. And these are the specific speed range values. These values you have to remember. Sometimes question is asked in the exam like which turbine is most suitable here. So based upon given data you have to calculate specific speed and then see in which range this specific speed is falling. Okay. One more important thing to note here is to calculate specific speed, power you should take in kilowatt. This is very common mistake. Many students take power in watt, so they will get different answer. Power should be taken in kilowatt. Another thing is in case of multi-jet Pelton turbine, suppose Pelton turbine is having more than one jet. So in such case you should take power per jet basis because these values are calculated like this. Power per jet basis only you have to consider. And in case of head, no need to remember these numbers. I have given these numbers just to have rough idea. High means how much high. So there is quite large variation, 50 to 1500. In case of Francis turbine, 25 to 350. So there is quite large variation. Simply if you remember, Pelton turbine is high head turbine, Kaplan turbine is low head, and Francis is medium, that is good enough. So discharge is reverse, like Pelton turbine is a low discharge turbine because if you observe the construction of Pelton turbine, the discharge will be coming out of nozzle. Nozzle area is small, so it cannot handle very high discharge. As flow area is limited, Pelton turbine is low discharge. In comparison with Kaplan turbine, if you see, in Kaplan turbine, discharge passes through between casing and hub of turbine. So flow area available is very large, so it can handle high discharge. And as I mentioned earlier, you need not remember these head values because we are not going to select turbine based upon head. Turbine is always selected based upon specific speed. Just to have rough idea, these numbers are given. Hello students, today we will discuss important concept of draft tube. Many students will have confusion regarding what is exact function of draft tube. Okay, there are two main functions of draft tube. First, I will list those functions, then we will discuss in detail how draft tube performs those functions. First function is it allows installation of turbine above tail race, without effective loss in net head. Okay, so let us understand what is meaning of this statement. See, the lower reservoir, this is also called tail race. To extract maximum possible available head, we should install this turbine as near to the tail race as possible. Okay, so that we can extract maximum elevation difference, maximum head we can extract. But in reality, it is always not possible to install this turbine near to the tail race. Why? Because tail race is some reservoir, right? Its level of water is not fixed. In rainy season, this level may increase. If level increases, then what happens? There will not be any problem to the turbine because turbine runs on water. If water goes into turbine, there is no problem. But turbine and generator both are mounted on same shaft. Okay. If water goes inside this generator, the generator will have electrical windings. There will be problem to the generator. Apart from that, for governing, there are various electronic devices are used. those devices will get damaged. To avoid that damage, we should install turbine above tail race. There should be some gap between turbine and tail race level. But if you are installing this turbine above tail race, we are losing this much amount of head. Head equivalent to HS will be lost if you don't use draft tube. And this loss will be very significant for Kaplan turbine, because you may be knowing Kaplan turbine are low head turbine. So they work on head as low as 5 meter, 10 meter like that. So suppose total head available on the turbine is 5 meter, out of which 2 meter you are losing because of draft tube. So head available will be only 3 meter. That is huge loss. Okay. So especially in case of Kaplan turbine, we must employ draft tube, because otherwise the head loss will be very significant. This is first function. Okay. If you install draft tube, this lost head will be recovered. How it is recovered, that part will study separately. Okay. But it allows the installation of turbine above tail race without effective loss in net head. If you use draft tube, there will not be loss of this HS. Second function, this recovers kinetic energy loss at exit. But partially. See, water discharging into the tail race, it will also have some kinetic energy. We are not utilizing that kinetic energy. That kinetic energy is lost as it is inside this tail race. If you use draft tube, we are going to recover that kinetic energy, not completely but partially. How this is recovered, that we will study separately. So these are the two main functions of draft tube. Now, before going into the details, let us understand what is meaning of these terminologies. Okay. Let us say 1 dash is exit of penstock. I am deliberately not using notation 1, because notation 1 is reserved for turbine inlet. Runner inlet is 1. This is not runner inlet. This is exit of penstock. After penstock, water will be going into casing. After casing, guide vanes. After guide vanes, then runner will come. Okay. That's why 1 and 1 dash are different. 1 dash means exit of penstock. Similarly, 2 dash is inlet to the draft tube. 2 is different. 2 dash is 2 is exit of runner. So 2 dash is inlet of draft tube. In between these two, there will be some gap. Okay. So velocities and pressure values between 1 and 1 dash may be different. So velocity and pressure at 2 and 2 dash may be different. 3 point is exit of draft tube. Now, if you observe in terms of energy, turbine is work producing device. Am I right? It will produce mechanical work, and that mechanical work comes at the expense of energy of a water. If you compare energy of water at inlet, that is at point 1 dash, and energy of water at point 2 dash, 1 dash energy must be higher, because part of that energy is converted into mechanical work and remaining is available at point 2. Please remember, energy at 1 dash is greater than energy of 2, because water is losing that energy, and that part of lost energy is getting converted into mechanical work. So energy of fluid at point 1 is in which form? At point 1 there will be some pressure, there will be some velocity, will be some elevation. Energy of a fluid is always measured in terms of Bernoulli's head. Bernoulli's head means sum of pressure, kinetic and potential energy head. So let us say Bernoulli's head at point 1 dash is B1 dash. B1 dash means P by rho g plus V square by 2g plus Z at point 1 dash minus B2 dash. So this difference represents energy head lost by water, and this we can consider as input to the turbine. Okay, you can consider this as an input head to the turbine. In terms of head, this is energy input to the turbine. Higher the energy input, more will be the energy output. Okay. Now, If you observe point 1 dash and 2 dash, elevation difference between these 2 points is not so significant. So Z1 dash and Z2 dash are nearly same. Similarly, if penstock diameter and drop tube diameters are nearly same, then velocities will also be same because discharge is same. Q1 is equal to Q2. So velocity will be same if these diameters are same. These diameters are not exactly same, these are nearly same, but velocities are also near to each other. So mainly this difference is arising because of pressure difference between point 1 dash and 2 dash. Why only pressure difference? Because elevation difference and velocity difference are not significant. That's why it is approximately equal to pressure difference divided by rho g. So what you can conclude is, more the pressure difference across turbine, more is the energy input. So to increase energy input to the turbine, we should increase pressure difference across the turbine. Okay. So what the drop tube does is, it plays with pressure at point 2 dash. How it works, we'll see now. To understand the working of drop tube, let us apply Bernoulli's equation between inlet of drop tube and exit of drop tube. So as per Bernoulli's equation, P by rho g plus V square by 2g plus Z at point 2 dash is equal to P by rho g plus V square by 2g plus Z at point 3 plus frictional head loss inside drop tube. HFD is head loss inside drop tube. Okay. Value of pressure at point 3, this value will be atmospheric pressure plus rho g y. Okay. This elevation difference is y. So atmospheric pressure plus rho g y. Okay. Z2 dash, this value, elevation difference between these 2 points, you can take Hs plus y. Okay. Take point 3 as the reference. So Z3 will be 0. Okay. So I'm writing this as P2 dash by rho g plus V2 dash square divided by 2g Hs plus y. This will be equal to PATM divided by rho g plus y plus V3 square divided by 2g plus HFD. Okay. So here y will get cancelled. You can rearrange these terms. So I'm writing this as P2 dash divided by rho g is equal to atmospheric pressure divided by rho g minus Hs plus V2 dash square minus V3 square divided by 2g minus HFD. Okay. You can check these calculations. So Hs is going on right side, so it will be negative. So V2 dash square is going on right side, again it is negative. So but here overall minus sign. So HFD is positive here, so here minus minus, it will become again positive. So correct. So this is, let us say, equation number 1. Okay. Let us analyze this equation carefully now. Hs is positive term. Among V2 dash and V3, V2 dash will be higher because here area is less and inside drop tube area increases gradually. Okay. So V3 will be less. So second term is also positive. As compared to first and second term, third term will be small. So overall value of this bracket will be positive. So we are subtracting positive value from atmospheric pressure. So from here we can conclude that P2 dash is less than atmospheric pressure. Okay. So what drop tube basically doing, it is playing with pressure at point 2 dash. If we don't use drop tube, then at point 2 dash pressure is atmospheric pressure, and if you use drop tube, pressure at point 2 dash is less than atmospheric pressure. And in terms of energy, lower pressure at exit of turbine is better. You can understand from this equation. Input head is nearly equal to pressure head across the turbine. If you decrease P2 dash, input head is going to increase. If input is more, output will also be more. Okay, so what draft tube is doing is it is reducing pressure at exit of turbine. So that's why pressure difference is increased. More the pressure difference, more the energy difference. Okay, now let us understand the meaning of each term. This HS, it represents recovery of lost head. Okay, what is meaning of this? If you don't use draft tube, we are going to lose head equal to HS. So this HS will be lost if you don't use draft tube. But if you use draft tube, what this draft tube is doing? It is reducing pressure at point 2 dash. The reduction in pressure is directly proportional to the HS. That's why this HS will be recovered completely. Okay, let us understand meaning of this second term. This second term represents partial recovery of kinetic energy loss. What is meaning of this? If you don't use draft tube, kinetic energy which is going into the tail race as a waste, that is V2 dash square divided by 2g, that is kinetic energy head. If you use draft tube, kinetic energy going into the tail race is proportional to V3 square divided by 2g. V3 square by 2g is less as compared to V2 dash square divided by 2g. That's why we are reducing kinetic energy loss. See, by using draft tube, we are not completely eliminating kinetic energy loss. Still, some kinetic energy corresponding to V3, it is going into the tail race. But what we are doing, we are minimizing this loss. Okay, so this decrease in kinetic energy, this is called partial recovery of kinetic energy loss. And this kinetic energy loss, how it is recovered? The pressure at point 2 dash, it is reduced proportional to this also. So this represents partial recovery of kinetic energy. Now with the use of draft tube, we are introducing this additional head. Okay, it is undesirable, but it will be introduced. So now you can understand how draft tube is recovering lost head HS also, and how it is recovering kinetic energy. What it is basically doing is, it is playing with pressure at point 2 dash. Lower the pressure, it is better because it is increasing pressure difference and energy difference across turbine. I hope you understand the working of draft tube. Let us see now how efficiency of draft tube is defined. So first, let us have a look at this equation. The first term in the bracket, it represents recovery of lost head HS. Second term represents partial recovery of kinetic energy head. For 1 minute, you can pause video and you think if draft tube is straight, what will happen? So instead of diverging draft tube, I have used draft tube of uniform cross section. What will happen? Okay, if draft tube is having uniform cross section, here V2 dash and V3 will be same. Okay, if these two are same, there will not be any recovery of kinetic energy. However, HS will be recovered. Still, if you apply Bernoulli's equation between these 2 points, everything will be same. Only V2 dash and V3 are different. So that's why this term will vanish, but HS will be present. So it implies even though draft tube is straight, it will recover lost head HS. Only thing is, it will not recover kinetic energy. Okay, so that's why efficiency of draft tube is defined based upon how efficiently it is recovering this kinetic energy head. So this point is important because any shape of draft tube is going to recover lost head HS. Okay, draft tube efficiency is defined, that's why only based upon how efficiently it is recovering kinetic energy. So there are 2 different types of definitions which are used in different books. So both the definitions are followed in standard books. So I'll discuss those definitions. So first definition, let us say definition 1. Okay, so this first definition is, it is defined in this way: draft tube efficiency is equal to actual recovery of kinetic energy head divided by kinetic energy head at inlet of draft tube. Okay. So it is like this. Kinetic energy head at inlet of draft tube. Here, whatever energy head is available here, that is considered as input. So out of which how much is recovered? Okay. So denominator is V2 dash square divided by 2G. So what is numerator? Actual recovery in kinetic energy head. So this is theoretical recovery. Actual recovery will be theoretical recovery minus HFD. So V2 dash square V3 square divided by 2G minus HFD. So this is first definition. Okay. Second definition we'll see now. The second definition is defined in this way. Numerator will be same. Numerator is actual recovery of kinetic energy head. Denominator is different. So denominator is taken as theoretical possible recovery. Okay. What is theoretical possible recovery? See, for a given areas, suppose A3 is greater than A2, still A3 at point 3 velocity will not be 0. There is certain velocity. Okay. So this is theoretical possible recovery. We cannot have we cannot have recovery more than this. Okay. So denominator is considered as theoretical recovery. This is denominator. Okay. In case of first definition, denominator is kinetic energy head at inlet, but it is not possible to recover this kinetic energy completely. So theoretical recovery is V2 dash square minus V3 square divided by 2G. Numerator will be same, V2 dash square V3 square divided by 2G minus HFD. Okay. In exam, which definition you have to use now? Okay. If you see the previous question, previous ESC question, so both the definitions they have used. Some questions will get answer by using definition 1, other questions will get answer if you use definition 2. So both the definitions you should remember. If you get theory question like subjective question on draft tube efficiency, so I recommend you to use both the formulas, calculate efficiency by both the methods. So let us examiner decide which definition he requires. Okay. So you remember both the definitions and you calculate answer based upon both the definitions in subjective questions. If objective question is coming, then first you try to use first definition and see whether your answer is available in option. If it is not available, then you try definition 2. So you should get answer based upon any one of the definition. Hi everyone. Now we are going to discuss cavitation in turbines. This phenomena little bit we have discussed in first chapter. If minimum pressure in the fluid, if it falls below vapor pressure, then cavitation starts. Am I right? Cavitation starts. What is meaning of cavitation? Cavitation means formation of vapor bubbles. Okay. Fine. We have discussed while discussing theory of the draft tube that minimum pressure is present at the exit of turbine or at the inlet of draft tube. If you remember, we have discussed equation P2 dash divided by rho g is equal to PA divided by rho g minus HS plus V2 dash square minus V3 square divided by 2G minus HFD. The overall value of this bracket is positive because HS is large, V2 dash will be larger than V3. So overall value of this bracket will be positive, since the first and second terms are having much larger magnitude than the last term. So this equation indicates that P2 dash is less than atmospheric pressure, and if this pressure falls below vapor pressure, then cavitation starts. Okay. You can think in terms of runner blade also. So if this is turbine runner blade, let us say in this direction turbine runner blade is rotating. Let us say this is runner blade of a Francis turbine. So this point is 1, this point is 2 dash, 2 sorry. So there is slight difference between 1 and 1 dash. 1 is exit of penstock, whereas 1 dash is inlet of turbine runner. So there is a difference between 1 dash and 1. Similarly, 2 is exit of turbine blade, whereas 2 dash is inlet of draft tube. So in between these two, there will be some gap or distance, we can say. There is slight difference between these 2 points. Okay. So many students will know that the pressure is minimum at the exit of turbine, that is at point 2, or at the inlet of draft tube, that is 2 dash. So 2 and 2 dash will have near about same pressure. Okay. So many students will know that the chance of cavitation is highest at the exit of turbine. But if someone asks you on which side of turbine runner blade, on concave side or on convex side, the chance of cavitation is highest. So you can think in terms of pressure in this particular case. The turbine is driven by fluid, right? The turbine is driven by fluid. There is a change in momentum of the fluid, due to which force is being exerted on the turbine blade. And how this force is transferred? This force is transferred through the pressure. So when fluid is passing through this passage, the fluid will be exerting pressure on this turbine blade. So on concave side, will get higher pressure as compared to convex side. So plus indicates on this side we are having higher pressure, whereas minus indicates on this side we are having lower pressure. So if you look at this turbine blade, so on convex side of the turbine blade, here pressure is minimum. So in this zone pressure is minimum. So here chances of cavitation are more. Okay. When cavitation starts, what happens? When cavitation starts, vapor bubbles are formed. Okay. Vapor bubbles are formed, and then when these vapor bubbles go in high pressure zone, these bubbles will collapse. These bubbles will collapse, and very high velocity microjets are formed. When these microjets strike on turbine components, various turbine components, then that can cause damage to the component. How? You can think in this way, that I am taking some surface, and on that surface I am striking small sand particles with very high velocity. So when sand particles are hitting on the surface with very high velocity, so due to force exerted by these sand particles, there will be erosion to the surface. So similar damage can be caused by these microjets. When this bubble collapse, surrounding fluid rushes in to fill this cavity, due to which very high velocity microjets are formed, and due to that there is a damage to the surface. So this kind of damage is called erosion. Okay. So to avoid cavitation, what we should do? We should ensure that this minimum pressure is greater than vapor pressure. There is another term which is related to the cavitation, is Thomas cavitation factor. Okay. Thomas cavitation factor. Cavitation factor. It is indicated by sigma. So sigma is basically a dimensionless number which is used to check cavitation. Now how this sigma is defined? Sigma is defined as HA minus HS minus HV divided by H. What is HA here? HA is atmospheric pressure head, PA by rho g. What is HV? HV is vapor pressure head, PV divided by rho g. What is HS? HS is height of draft tube. Height of draft tube. And H is net head on the turbine. net head on the turbine. Okay. So this is a dimensionless number. One more point to note here is, in case of cavitation factor for turbine, vapor pressure head, not vapor pressure head, frictional head loss is not considered. Okay. So only HA, HS and HV. In case of pump, in addition to this HV, here we'll write minus of HF inside suction pipe. But that is not considered in case of turbine. Okay. This is how it is defined. Okay. This Thomas cavitation factor, it is also used to check cavitation. The basic condition for cavitation is, if minimum pressure falls below vapor pressure, then cavitation starts. But this vapor pressure will change from location to location, because from location to location fluid temperature will change, and if fluid temperature changes, vapor pressure will change. That's why this dimensionless number is defined. So turbine manufacturer performs extensive testing on the turbine, and he will calculate the value of sigma for which cavitation starts. That is called critical cavitation factor. Okay, critical cavitation factor. Let us say it is indicated by sigma c. So this critical cavitation factor means, if sigma value becomes equal to sigma c, at that moment cavitation will start. And at the installation of turbine location, suppose here we need to install turbine, so here we will calculate value of sigma. If this value of sigma falls below this critical value of cavitation supplied by turbine manufacturer, in that case cavitation will start. So these two conditions are equivalent to each other. These two conditions are equivalent to each other. Whenever minimum pressure falls below vapor pressure, cavitation will start. At the same moment, sigma value falls below sigma c. Okay, but the point here is, why sigma we are using? PV will change from location to location, whereas sigma c will be property of a turbine. For a given turbine, sigma c value will be fixed, so it will not change. That's why this Thomas cavitation factor is used. Please try to understand this question. This question is asked based upon similarity laws. If you see the previous GATE questions, maximum questions on hydraulic machines part come from this similarity laws, and there are three simple similarity laws. Okay, so first similarity law is ND is directly proportional to root H. Second similarity law, QV is directly proportional to D square root H. And third similarity law, power is directly proportional to D square into H to the power 3 by 2. So most of all the questions from this similarity law you can answer based upon these three equations. Now read this question. Try to understand the given data. A model of a hydraulic turbine is tested at a head of 1/4 that under which full scale turbine works. Okay. So given data I am listing here. So this 1/4, what is this 1/4? Head of model divided by head of prototype. Okay. The diameter of model is half of that of full scale turbine. So half is what? Diameter of model, dm divided by dp is 1/2. Agreed? If n is RPM of full scale turbine, so this n is RPM of full scale turbine. Full scale turbine means prototype. Prototype RPM is n. What do you have to find out? Then the RPM of model will be, that is Nm. Speed of model turbine we have to find. So look at this given data. We need to find out speed. So among these three similarity laws, we have to use first similarity law, because speed is present in first similarity law. Agreed? So ND is directly proportional to root H. Therefore, Nm into Dm divided by Np into Dp equal to root of Hm divided by Hp. Now substitute the values. Nm we have to find. Np is equal to n. Dm by dp 1/2. Hm by Hp 1 by 4. Now this 1 by 2 and root 1 by 4, it will get cancelled. So what will get? You'll get Nm equal to N. Model speed and prototype speed both are same in this particular case. So answer is C. Read this question. This question is asked based upon specific speed. I am reading the statement now. Consider two hydraulic turbines having identical specific speed and effective head. So specific speed is same and net head is also same. If the speed ratio N1 by N2 of the two turbines is 2, then the respective power ratio P1 by P2 is. Okay. So specific speed is given same, Ns1 is equal to Ns2. What is formula for specific speed? N root P h to the power 5 by 4 for first turbine is equal to N root P divided by h to the power 5 by 4 for second turbine. Now in the question it is mentioned that effective head is also identical. So head will get cancelled out. Okay. So what will get here? N1 divided by N2. N1 root P1 is equal to N2 root P2. What we need to find out? P1 by P2. So P1 divided by P2 will be equal to N2 divided by N1 whole square. Okay. What is value of N1 by N2? 2. See here, this is N1 by N2. In our equation, it is N2 by N1. So this will be 1 by 2 whole square. So answer you should get 0.25. So simple question was asked for 1 mark. Same question you can solve by using similarity laws also. The formula for specific speed, in fact, it is derived from similarity laws only. So power is involved here. So third similarity law we have to use d square h to the power 3 by 2. But we need relation in terms of power and speed. So we have to correlate power with speed. So for that, first similarity law we have to use nd is directly proportional to root h. Now from these two equations we can eliminate the diameter. Diameter is not given here. Head and speed, their relations are given. Diameter is not given. So diameter will eliminate. So d will be nd is directly proportional to root h. So d will be directly proportional to root h by n. So therefore substitute in this power equation, power will be directly proportional to root h by n square into h to the power 3 by 2. So this is directly proportional to h to the power 5 by 2 divided by n square. So head is constant. So ultimately you will get power is inversely proportional to n square. So from there also you will get identical answer. Look at this question. This question is also related to similarity laws. A hydraulic turbine develops 100 kilowatt power for a head of 40 meter. If the head is reduced to 20 meter, the power developed in kilowatt is. Okay. 1000 kilowatt power is obtained when head available is 40 meter. When head is reduced, naturally power has to go down. So third similarity law we have to use, power is directly proportional to d square into h to the power 3 by 2. Now turbine is same. It's not model and prototype kind of thing. Turbine is same. That's why I can write power is directly proportional to h to the power 3 by 2. Therefore, P2 by P1 is equal to H2 by H1 to the power 3 by 2. Therefore, P2 is equal to P1 is 1000 into H2 by H1, 20 divided by 50 to the power 3 by 2 is 1.5. If you do this calculation carefully, you should get answer near to 354 kilowatt. So answer is B. Look at this question. This question is again based upon similarity laws. You can read this question by pausing video and try to understand what is given data. A test is conducted on 1/5 scale model. 1/5 scale model means size of model is 1/5 that of prototype. dm by dp is 1/5. Under a head of 2 meter and volumetric flow rate of 1 meter cube per second at 450 rpm. Now think carefully and tell me, this 2 meter and 1 meter cube per second and 450 rpm, these are the conditions for model or prototype. Read this statement carefully. A test is conducted on 1/5 scale model. Test is conducted on model. So those are the conditions for model. So HM is given 2 meter. QM is given 1 meter cube per second. NM is given 450 rpm. Okay. So density is given 1000, G is 10. Assume no losses. Assume no losses both in model and prototype turbine means their efficiencies we have to take 100%. That is the meaning of this sentence. The power in megawatt for full scale turbine working under head of 10 meter is. So HP is given 30 meter. HP is given 30 meter. What we need to find out? Find power in megawatt for full size turbine. That means PP we have to find. Okay. As we require power, we need to use third similarity law. The power is directly proportional to D square into H to the power 3/2. PM divided by PP is equal to DM divided by DP whole square into HM divided by HP to the power 3/2. We need to find out PP. DM by D, this ratio is given 1/5. HM by HP, HM is 2, HP is 30 to the power 3/2 is 1.5, correct? We need to find out this PP. Now somehow we must know PM. If you are able to find out PM, then our question is solved. Think how to find out this PM. Here, assume no losses both in model and prototype turbines, means both efficiencies we have to take 100%. Power in model we can get as model efficiency into rho G QM into HM. So this efficiency we have to take 1. Rho G value given, QM HM given, so we can find out PP. So from here PP will get rho value is 1000 into 10, Q is 1, HM is 2, 5 square is 25 and this goes on right hand side. So 2/13, 1/15. So this is 15 to the power 1.5. If you do the calculations carefully, you will get answer 29.05 megawatt. Okay. So correct 2 decimal places he is asking and power in megawatt. So we should enter this answer as 29.05.